Yes, this is better.
Oh, I have here. That's something.
Okay, yes, that looks good.
Let's see. What's like this? Right.
Oh, yeah. I'm still waiting for. I thought that one.
I was born in Chicago. You're talking about. Nice class. Let me start. Now it's exactly 9 o'clock. I think that some people drunk maybe, but we cannot wait. So let me open this conference, Supersymmetry 50. I'm very happy to see all of you here. Supersymmetry 50 because the first works of Zumina were published in 1973 as preprints, and we're a little bit late because we wanted to do it a year or two ago, but because of COVID, of course, everything had to be canceled. And this correlates with our previous conference, which was called Supersymmetry 30, which was in the year 2000. That's the year when the first paper on, by Goldman and Liebman on supersymmetry in 4 dimensions appeared. 1970, yes. It appeared 1970 in the preprint form, and then 1971 was published in Russian journal. Of course, very few people at that time, at the time of publication, knew about this paper, but still, formally, it was the 2000 was the 30th anniversary. So that explains the names of the conference. You should think in your mind that this conference occurred, in fact, 2 years ago. But 2 years ago, everything was closed, so shut down.
So you need security happened because of for this purpose.
Well, at that time, I should say we had a little bit more guests. Unfortunately, many people who pioneered supersymmetry in its early years, 1970s, are no longer with us, and some people, thank God, are still with us, but they don't fly transatlantic, or no longer fly transatlantic. So that was a reason why some of them couldn't come. But nevertheless, I think that the exciting spirit of those days is now carried out by young people. Many of them I have even never seen, unfortunately, but I'm happy to see them now. And now we will start. I will be a chairman for the first session, and Arkady will be the second session after the lunch. And then I think maybe I will ask Zohar, who is also an organizer, to be a chairman tomorrow before lunch and so on. Unfortunately, Thomas Dumitriescu, who was supposed to come, who was the first organizer, suddenly had to cancel this visit because his son got sick. So, but we will remember about his important contribution too. Tonight at 6 o'clock, there will be a conference dinner. We all go, it's not far from here, within the walking distance, at most 5 minutes probably, maybe 6 or 7, but it's a big building which is in an irregular shape. You see, it's like a triangle. If you look from far away, you see a triangle, so it's easy to recognize it. Okay, the first, now we will proceed to the first talk of our conference. Francesco Benini from SUSY, quantum black hole entropy from ADS CFT. And you have 35 minutes, but the last 5 minutes are for questions. And please don't delay because our schedule is pretty tough.
So I'm using the common computer. The person managing the computers is here, or
Iliesiu she was here.
Let me.
she's set up.
You have a problem, right?
It is visible on Zoom. Just not sure if this is visible on Zoom. Open Acrobat, but I'm not sure if the oh. This is Acrobat. So
Oh, it actually opened? It wasn't opening before.
it's fine.
Yeah.
Oh, okay.
Yep. Yeah.
Okay,
fine.
great.
Go ahead.
So thank you very much. It is a great pleasure to kick off this conference to celebrate the 50 years of supersymmetry. And so supersymmetry was discovered at the beginning in string theory and in quantum field theory. And from the first papers, in particular papers of Vess and Zumino, this appears as a curious symmetry with some that leads to some interesting cancellation among one-loop effects. And soon, after a few years, this was understood in terms of non-renormalization theorems. And jumping ahead, nowadays SUSY has become an, I would say, irreplaceable tool to perform exact computation in strongly coupled quantum field theories. We don't have other many other tools that allows us for such exact computations, I would say. Of course, it also had a huge impact on gravity with supergravity and so on. But here in this talk, I would like to discuss an application of supersymmetry to gravity by going through quantum field theory. And of course, the link between these two subjects is SCFT. So we know that quantum gravity in de Sitter space can be given an unperturbable definition in terms of a boundary theory. And we can use this to compute some quantum effects in gravity by doing this computation in field theory. And we can ask many questions about many types of quantum effects. And here I would like to focus on the physics of black holes, in particular the black hole entropy. You know that the leading entropy to a black hole comes from the Bekenstein-Hawking entropy, which is the horizon area divided by 4G Newton. But then there are corrections that come from quantum effects. And in particular, we could define entropy as the logarithm of the number of microstates. So this is a good definition. If in field theory we can determine these microstates, then we can define what are the quantum corrections to entropy. Alternatively, we could directly try to compute gravitational partition functions and define them in terms of the boundary circuit. So by definition, the gravitational partition function is the one of the boundary theory. And once again, we can try to compute quantum corrections for it. In fact, holographically, we can take a black hole and we can think of it as a holographic RG flow, because far away we have some ADS, and then the black hole is a sort of a flow. And then in the near horizon, for instance, the black hole is BPS, and so extrema, there is another ADS2. So we can think of it as an RG flow. And then we can use the rules of AdSCFT to read off the behavior of the fields at infinity. This, by the rules of AdSCFT, will induce some deformation, some background in the boundary theory, and this will define as for us some partition function in the boundary theory that we can compute. However, if we want to work in a regime in which gravity is weakly coupled and close to Einstein gravity, then this means that the boundary theory is at large n, and more importantly, strongly coupled. And so in particular, we need some tool to do computations, and a perfect tool is supersymmetry. And so in particular, this suggests that we can compute some supersymmetric partition function. This is, for instance, some index in which we count states, but with -1 to the fermion number. So this gives some protected quantity that we can compute exactly, for instance, with localization techniques. Okay, so I would like to discuss, so I would like to tell you what is the status of our understanding of quantum effects for black holes, for BPS black holes. And I would like to do it in a specific example, which is one example in which we perhaps understand better these issues. And this example is the one of Kerr-Neumann black holes in ADS5. These are the Gutovsky-Real black holes. So these are some black holes that one can construct in 10-dimensional type 2B supergravity in ADS5 process 5, or directly in 5-dimensional gauge supergravity in ADS5. And these are some black holes which are rotating. They also have electric charges, in particular for the U1 cube, which is the Cartanov SO6. Well, they are BPS. So what can we do about these black holes? So as I said, we can try to count the microstates of these black holes in order to define quantum entropy. And in order to count states, we can use one of these supersymmetric partition functions, in particular the superconformal index. Computing in the boundary theory, which was in this example is 4-dimensional n equal 4 superior means. So here is the Hamiltonian definition of the index. This is a trace of the Hilbert space of the theory on S3. There is the -1 to the fermion number. There is some supersymmetric Hamiltonian, such that only the BPS ground state contribute. So this is protected. And then there are various fugacities for the angular momenta and some combination of the RCM. So these are electric charges. Okay, this is the Hamiltonian definition, or equivalently, one can give a Euclidean but integral definition in terms of the partition function on S3 times S1 with some suitable supersymmetric background, some flat connections. And for the future, let me say that I will use chemical potentials as opposed to fugacities. So I will use these variables sigma and tau and these deltas that are the electric chemical potential with some relation that is required by supersymmetry. So as I said, this is a protected quantity. So we have an exact integral formula for this superconformal index. The formula for gauge group UN is written here. So this is an integral over the gauge group. And then there is an object which is called platistic exponential. This function f that I'm not going to write is the so-called single letter index. Essentially, it counts the supersymmetric fields in the Lagrangian. And then this object, this object here is the character for the joint representation. So this object here just counts all possible multi-trace operators, BPS operators that one can construct, and this integral extracts the gauging invariant ones. So here we have a formula, and now we have to take the Lagrangian limit. So this is just a mathematical problem. However, this turns out to be a tricky problem. And in fact, in the last 5 years, various methods have been devised to understand, to compute the Lagrangian limit of this formula. And here we'll focus on just on one. This is called Bethe-Ansatz formula, is an alternative formula for the same quantity. It's just a rewriting of this formula here. Now there is no integral in this formula, but there is a sum. And this is a sum over the solution set of certain transcendental equations that looks like Bethe-Ansatz equations for some integrable system. And the unknowns in these equations are complexified holonomies. So these are complex variables that corresponds to the Cartan of the gauge group. So here is the gauge group, once again, is UN. And one is supposed to compute these, find these solutions, and then plug it back into this function that I'm not going to write and compute the result. So what do we know about these solutions? Well, we know about some discrete families of exact solutions. These are labeled by two integers, m and r. In particular, m is a divisor of n, then r, there is some discrete values. There are also some other solutions that I will not, essentially will neglect because these solutions are not very well understood. So in the rest of the talk, I will neglect the solution and I will come back to them at the end. But so, okay, so what we have to do, we have to solve this equation using this solution, plug in here, compute the Lagrangian limit. And when we do that, we find something that looks like the following. It's a sum over these solutions, and we can compute the Lagrangian limit of each of the contributions. And it turns out that each contribution goes like e to the n squared. So this looks like some semi-classical expansion because order n squared is like a classical action in gravity. So this looks like a sum of the contribution from some classical solutions. So in fact, we can compute the Lagrangian limit of each of these contributions. And here is the result. And so what I would like to do is to describe a little bit this formula, this result, and in particular make connection with what happens in gravity and try to understand what we can match or what we can learn from this computation.
Francesco,
Yes.
the log n, what is the interpretation of log n in the 1/n expansion? You have a log n contribution.
Yes, so I mean, this comes from the expansion of this contribution. So you do your expansion.
No, I understand technically, but what I mean is what the interpretation in terms
Gravity.
Yeah.
Yeah, I will describe that. This is precisely what I want to do in the next 10 minutes. So going through these various terms and explain what they correspond to.
So there is no limit of Lagrangian. I mean, it doesn't go to it because it grows. This UI will proportional to n.
Well, there is an n squared. So this is the leading term. N squared.
Yeah.
Then in principle, there is a 1/n expansion
Yes.
that interestingly truncates. So there is just order n, the coefficient is 0. Then there is an order 1, and then it truncates. Then there is a log n that we described. This is also order 1. And then there are some exponentially small corrections. And what I want to do is to briefly explain what they correspond to. Okay, very good. So here it's, in fact, as I'm writing, there are some p's that can be interpreted as a non-shell action, some terms that can be interpreted as higher derivative, something that perhaps can be understood as one loop, and then something that can be understood as some stringy objects, say. Okay, so let me explain. So first of all, as I said, we want to reproduce the leading contribution to the entropy of a black hole, which is Bekenstein-Hawking. And in fact, you can take one of these solutions that I call 1, 0, and you just keep the leading contribution in the large n limit. It goes like n squared. And here I'm just rewriting it. So it's this contribution here, but I'm rewriting in a more legible way. I'm calling x the square brackets, these functions here. In fact, what these square brackets do, there are some discontinuous function that shift the argument by an integer. So let me just call this x. So it's a very simple expression. In fact, this is sometimes called the entropy function, but in fact, it's the free energy of the black hole, because if you compute the Lejeune transform of this function here, you precisely obtain the Bekenstein-Hawking entropy of the black holes as a function of the electric charges and the angular momenta. So I'm not going to write this expression here, but this precisely gives you the Bekenstein-Hawking entropy. So this is good. The leading contribution comes out of the superconformal index from a computation in the boundary theory. What else? So now we can take another piece. So let's add this piece here, which is order 1 in n. And if you put them together, you discover that you get a correction. So you get an expression of the same form, but there is a correction. Instead of n squared, now you get n squared minus 1. And so in this particular example, there is no order n. But if you do it on other geometry, that is due to another field theory, you will get essentially also an order n contribution that can be written in terms of the central charges of the boundary theory, A and C. So can we reproduce this from gravity? And the answer is yes. This was understood by Cassani, Rui-Perez, and Turetta. What you can do, you can look at the 5-dimensional gauge supergravity, and you can add higher derivative correction. You can add a 4-derivative correction. And what happens is that, in fact, the 2-derivative action has a coefficient that gets corrected at order 1. And moreover, you have this 4-derivative term, which is essentially unique. And the nice thing about these two terms is that each of them contains a Chen-Simons term. This is a A-wedge-F term, this is a A-wedge-R. And these Chen-Simons terms are directly related to the anomalies by the SCFT, to the anomalies for the R symmetry. So the coefficients of these two terms can be fixed in terms of R symmetry anomalies or central charges. And so now the coefficient of these two terms is fixed. And now you can go on and compute the on-shell action of these two guys in the black hole background. And the result that you obtain is precisely this expression here with this correction. So this correction is reproduced by higher derivative corrections in the back. Okay, very good. So what about the next terms? So let me go back. So what about these terms here?
Francesco,
Yes.
it should also be perhaps understood why it truncates.
No, I would say no.
You think it should not be explained?
So one way in which it could be explained, but I mean, this is just speculative, is that you might find that further higher derivative corrections are D terms.
Yes.
And then when you compute the on-shell action, they do not contribute.
But it was proven on field theory.
What do you mean field theory?
On the field theory side, I think it's proven that there are finitely many.
Yes. On the field theory side,
gravity was.
yes. In the field theory side, yes. Gravity. Sorry.
Maybe it should be explained.
Yeah, as I said, one possibility in gravity is to show that these other derivative terms are D terms.
D terms of this particular black holes.
Yeah, so they do not contribute to this partition function. To another partition function would contribute, but not this one, which is supersymmetric. But this has not been proven, at least in this setup, as far as I know. Okay. So what about these terms here? So there is a log n, And then there is this term here. Now the log n can be understood as the fact that in gravity there is a cigar, because there is compact time and then there is the radial direction. So as in any Euclidean black hole, there is a cigar. And so in type 2B string theory, there is a B2 field, and you can have flat connections of this B2 on the cigar. This connection can take n values. So if you sum over them, you get n copies of the same contribution. So this explains this log n. And it can be understood in field theory as the fact that it's a spontaneous broken one-form symmetry that gives this log n. So this was also mentioned in paper of Zohar from the field theory side. What about this term here? So this term here has not been understood. We expect that this should come from a gas of gravitons in the black hole background. In fact, this contribution looks very similar to the contribution of a gas of gravitons in ADS that was computed a long time ago by Maldacena and collaborators. This is similar, not quite the same. So we expect it should correspond to this gas of graviton in the black hole background, but this computation has not been done. Okay, what else? So this was just for one contribution to the index, but in fact there are many contributions to the index. This is the sum of the solutions. So what about them? Well, gravitationally, what we expect is that we fix the boundary conditions that here are S3 times S1 for the superconformal index, and then we should sum over all bulk solution with the same boundary conditions. And in fact, it turns out that there exists an infinite family of complex Euclidean solutions, some of which are orbifolds of type 2B supergravity, that are supersymmetric but not extremal, and this is possible because they are complex, and that have the correct boundary conditions. And in fact, it turns out that these solutions depend on some continuous parameters that identify with the chemical potentials at the boundary, but the chemical potentials at the boundary are only fixed in terms of up to a shift by integers. Instead, the solutions in the bulk completely change if you change these solutions, if you shift them by an integer. And so this gives an infinite number of contributions of solutions with the same boundary conditions. And for each of them, you can compute the on-shell action. And here's the result. As you see, it looks very similar to what I had before. This is the n squared contribution. There are these shifts of the variables. So this is the correct form, but unfortunately, there are too many solutions. Because here we have to sum all these arbitrary shifts, while in the field theory formula, we don't have all these arbitrary shifts, because this bracket function, in fact, does a shift, but it's a prescribed shift. You don't have to sum. So what does it mean? And this resonates with the fact that we know in complex analysis that usually when you do a saddle point, you have to take complex saddle points, but you don't have to take all of them, only some of them. And you can understand then that in terms of steepest descent. But here is field theory, gravity. So how do we understand which solution should be kept and which not? And a possible answer comes from non-perturbative corrections. So let me jump to that. It turns out that there are some Euclidean supersymmetric D3 branes that one can construct at the horizon. They wrap some S3 times S1. And you can compute the on-shell action for these D3 branes. It goes like N. And then you ask, okay, what is the contribution of these solutions? And what you have to do is you're supposed to sum over the pure gravity solution, then the solution with one D3 brane, and the solution with two D3 branes, and so on and so forth. And if the on-shell action of these D3 branes has an imaginary part which is positive, then this is exponentially small. And so this looks like a non-perturbative correction to the on-shell action. And in fact, if you compare the action of the D3 branes with what you compute in field theory, well, let me go back. This is precisely the same. So the instant on action, if you want, is the same. The prefactor has not been computed, but the instant on action is the same. However, suppose that now there is some D3 brane for which the imaginary part of the action is negative, then this is exponentially large as opposed to exponentially small. And when you sum all of them, you get a divergence. So this suggests that there is D3 brane condensation. this modifies the classical solution, and you should flow to a different classical solution. So this gives a criterion for which complex saddles should be retained and which should not. The criterion is that only those for which all Euclidean unitary branes have imaginary part of the action which is positive. And if you apply this criterion to the gravity solutions, you see that most of them are excluded. Only the ones that are kept are the ones that indeed appear in the expansion of the index. So there is a nice match, and you solve that problem. Okay, so this concludes this part. And now, very briefly, a couple of minutes, I would like to go beyond supersymmetry. And in fact, in the last few years, there's been a discussion of interesting quantum effects that have been observed in near extremal and near BBS black holes, effects that come from some universal zero modes in the near horizon region. However, these effects happen at very low but positive temperature. And they are controlled by a Schwarzian or super Schwarzian action. And Luca in his talk, we spent a few minutes discussing them, so I will not discuss these effects here. But the question that I want to pose is, can we actually extract or compute these quantum effects from the field theory point of view, and then try to compare with what has been argued in gravity? But in order to do that, we need to go beyond supersymmetry, because they say these are effects that happen at positive temperature, not zero temperature. And in fact, this effect has been observed in some two-dimensional CFT, but using modularity. In higher dimension, we don't have modularity, so what can we do? And the idea that I want to put forward is that, okay, we cannot use the index, because the index counts supersymmetric states. It's only applicable to BPS black holes. But instead of computing the partition function, we can use the very same supersymmetric background, but keep the Lorentzian signature, so some time direction, to do a reduction. And this should give an n equal to super quantum mechanics. Now, the super quantum mechanics will have some ground states. These will be the BPS states of BPS black holes. But we can try to compute excited state. And this should correspond to the states of near BPS black holes. And so we wanted to explore this possibility, and we started doing that in a specific example, which is some static black holes in ADS4. Black holes are easier because they are non-rotating, they are static. So they have magnetic charges, but they are not rotating.
There's no quantum mechanics at finite temperature.
Well, this is a quantum mechanics that you compute from the reduction, and then you can ask, okay, let me compute the spectrum. And of course, you can work in the microcanonical or grand canonical ensemble as you wish, but you try to compute the spectrum above zero. Okay, so essentially, let me just sketch the idea. So the idea is that you start with an index. This is the index that counts the BPS states in this particular setup. And here is the formula for the index. There is a sum over magnetic gauge fluxes, and then there is some integral. And the observation is that this integral looks like the Witten index of a quantum mechanics. So it looks like if you do the reduction, you get quantum mechanics, but you get an infinite number of sectors for this quantum mechanics. And so it's not very clear if this is a useful object. However, when you go to large n and you have exponentially large degeneracy, you expect that only one term in this sum will dominate. And so you can try to say, okay, let me just take that particular term and the quantum mechanics associated with that term. This is now quantum mechanics with a finite number of fields. So this might have interesting physical information. And so you can try to determine what this flux sector is using saddle point approximation, and then select a particular flux sector and do Kaluza-Klein reduction in this particular flux sector. Okay, so this is what we did.
Is this a two-sphere definition?
Yes, so we are, so ADS4, the boundary is three-dimensional, is S2 times R.
In your geometry, does it have a finite size or is it?
Well, in the boundary theory is finite size. Okay, holographically, it's this size, but
This particular sector that you found was also found by Sarah before. No?
by whom?
Sarah?
Sarah. Was good.
Yeah. She had also this, in this infinite sum over M, she found some particular M that dominates and gives the AVGM entropy. Maybe I got
Okay.
confused with it.
Sorry if I missed it.
I would not be maximizing, but yeah, we had some, but I would not.
So there was a paper of Zaffaroni and Osseini where to compute the index, they did the same computation. So they do set the point and they select one contribution. So here I'm taking the very same contribution, but I'm doing the reduction instead of just computing the index. Okay, so you can do the reduction. There is a particular theory that you have to use, is a 3D n equal to Chern-Simons theory. You do the reduction on S2. The only point I want to stress is that now there are Landau levels because there is magnetic flux. So there is a huge number of ground states, which are the Landau levels. And then there are massive states. If you're interested in very low temperature, you forget the massive states, you only keep the Landau levels. So let me give you the result. The result is the following. So in this quantum mechanics, so first of all, because of this flux, which is along the Cartan, it breaks the gauge group to U1 to the n from UN. And then both from the vector multiplet and from the chiral multiplet, you compute these Landau levels. And depending on the sign of the magnetic flux, you either get a chiral multiplet or a Fermi multiplet. And there are some that comes from the vector multiplet and some that comes from the chiral multiplet. But all of these fields are in the bifundamental representation for U1 to the n. So there will be charge on one U1 and another U1 because they come from the elements of a matrix. Because in the original, the UV theory, everything is in the adjoint. And okay, the only point, we can write down this quantum mechanics, the only point I want to stress is that, interestingly, so these Fermi multiplets contain a single dynamical fermion, similar to 2D. These chiral multiplets have an action, it contains only one derivative kinetic term for the bosons, and the fermion is auxiliary, so these chiral multiplets contain a single scalar. Okay? And you can construct this quantum mechanics. This quantum mechanics, we have not explored the physics of this quantum mechanics. The only thing that we did was to check that in fact the Witten index matches at leading n with the index of the 3D theory. So this quantum mechanics has the correct number of ground states to reproduce the BPS states of BPS black holes. And hopefully the spectrum above it will describe the physics of near BPS black holes, but we have not done it. So I think I'm out of time, so let me jump to the conclusions. So what I did was to show that in fact, precise computation that one can do in field theory with supersymmetry can be done and can match both perturbative and non-perturbative effects in gravity with very good accuracy. And in fact, also provide some predictions, for instance, about this criterion for which complex saddles one should keep or not keep in gravity. The match that I did is not complete yet because I neglected some continuous family of solution. So those should correspond to something in gravity that has not been identified yet. We have some ideas, but this has not been done. And then the other interesting question is about this supersymmetric quantum mechanics that we found. Does its low energy spectrum reproduce the physics of near BPS black holes? This has to be seen because this is an analysis that we didn't do, but hopefully it will lead to results. So thank you.
Well, we still have 4 minutes for questions, comments. Please, thank you.
When we have multiple saddle points in complex domain, to figure out whether the given point contributes to the path integral you start with or not, you cannot do it just by local analysis of the saddle point. You need to compute the steepest descent trajectory, like gradient flow, something like that, and then see if it will eventually bring you to the contour you start with. So it's a kind of a global analysis. And first step is figuring out how do you set up this gradient flow? So what kind of equations will you get? That's might be an extra dimension to the problem.
Yeah.
So I mean, you might be right by some miracle, but the suggestion was just out of head.
Yeah, no, I know. In complex analysis, steepest descent is what you have to do. In field theory, it's extremely complicated to do. Perhaps in Chern-Simons theory it's been done, but in general, it's very hard.
So, the theory of Hamiltonian, I don't think it has been ever done for its even for mechanics.
Yeah, so our suggestion that this might be a proxy for it because of some miracle, as you say. The only thing that we can say is that we have the field theory answer. We can compare. We know that the field theory answer is correct because there it was a correct.
In field theory, you also have multiple contours possible. So
Yes, but
so
the formula that yes, but the formula that I did is not a saddle point of the integral. Is this Bethe-Ansatz formula that is derived in a different way? So there's a specific contour that you have to choose, the Jeffrey-Keir one, and we did.
right, but so
use that.
that's I mean there is some magic there as well. But I'm just saying that in the field theory you start with, you might compute an index for different contours for the field theory path integral, and it will have give different answers. So those will be
Yeah, but I think the superconformal index. Let's see, I don't think that there is any ambiguity in the definition of the superconformal index.
Yeah, because you choose the contour at Hanslow for operators.
yeah, but they can choose different contours. So
Yeah.
when you do this analytic continuation, for example, go to this second sheet, third sheet. I'm not convinced that that's by that time you still remain the same contour.
No, I mean what you do in the superconformal index. So you start, you have a well-defined contour for a certain domain for the fugacities, and then by analytic continuation, if you change the fugacity, you are right. You have to adapt your contour in such a way that you have an analytic answer. But all of these can be taken care of, and this is taken care of by the field theory formula that they show. The ambiguity, as you said, is in gravity. So in gravity is just a wild proposal, and yeah, we see that it matches, but it's not clear why.
Okay, let's thank again the speaker. Next speaker was Nick Dorey, University of Cambridge, black hole entropy and superconformal quantum mechanics.
Do we have the right connector?
Huh?
That's the next question.
The only subtlety here is there is.
As we see. Let me try connecting to this and then see if that works. And the only challenge is going to be whether it works on Zoom as well.
Hang on, where's my?
Move to it. I don't know. Move it.
I can email you a PDF or something.
I don't know whose computer this is. So I'm not an organizer, just I'm a local. So I was hoping that I know. Yeah, I was hoping that I can figure it out. Let's see, this is HDMI, right? Oh, I see it. Hold on. This is gonna work. Give it a second. The challenge is that this might not do anything off of Zoom. As always, Zoom is the problem, right? Well, we're about to find out. No? Try disconnecting and reconnecting. Okay, so it's showing the. Okay, so I could disconnect the laptop and connect to this, which would almost certainly work, but then it's almost certainly not going to show up on Zoom. Hi, we're trying to connect a non.
Yes.
Yeah,
You disconnected Zoom.
we did. Yeah, right.
that purpose.
Would you want to zoom as well, or?
You shall see.
Right, thank you so much for the invitation to speak here. I don't think I've been here for 30 years. I remember coming here and giving a talk about baryon annihilation maybe 30 years ago. And it's a very fond memory. So I'm going to talk a little bit about some work with my student Andy Zhao and also Rishi Muland, who's a postdoc in Cambridge. So I'm going to talk about something that's one of the classical achievements of supersymmetry over its 50 years, which is success in reproducing the entropy of black holes from the counting of BPS states. But I'm going to talk about it in a particular context. And that's the context of finite dimensional holography. So here I have in mind circumstance. We heard a lot about, in general, when we apply SCFT, we're normally talking about dualities between full quantum field theories and gravity. But there are some cases we know of already where we have gravities between finite dimensional quantum mechanics and a gravitational dual. So the most famous example probably is the BFSS matrix model, which has a regime of parameters and states in which it has a gravity dual in 2A, and that, for example, is something you can investigate with numerical simulations. And in general, finite dimensional holography in this sense is super interesting for among many reasons, but in particular, it has the prospect of something that can be investigated on computers, either now or in the future. But something's missing, which is the application of those methods that I mentioned in my opening remark, which is in the context of finite dimensional holography, can we perform an analytic check in which we reproduce the Bekenstein-Hall area of entropy of a black hole from a quantum mechanical dual? And I mean here a finite dimensional quantum mechanical dual. And I'm thinking of a setup in which the quantum mechanics is dual to the whole of the gravity theory, not just the BPS sector. So in this talk, I'm going to talk about exactly such a match in the context of superconformal quantum mechanics, a particular superconformal quantum mechanics, and reproducing as part of a more general story to do with dualities between particular kinds of quantum mechanical models and what are called ultra-spinning black holes. And I hope I'll have enough time to say a bit about each of those things. But I'm going to start by reviewing some of the basics of the models which I'm going to be working with, which are conformally invariant quantum mechanical models. So if we just start with the simplest possible setup of a quantum mechanical sigma model, and we ask what it means for it to be conformally invariant, in general, we should ask that the target manifold certainly will have some scaling invariance. And this generally means that we're thinking about a target which is non-compact to be scaling invariant, and generically it's going to also be singular, and that's a problem we'll have to discuss and address as we go on. So in fact, generically it has the form of a cone. If you have such a scale invariant metric, the conditions under which the sigma model acquires a conformal invariance were investigated by Strominger and Michelson. And the story is a nice one. In addition to the Hamiltonian, which is represented in the usual way as the Laplacian, you need to have, for scale invariance, a homothety or homothetic killing vector. And under those circumstances, you get, when you have what's called a closed homothety, then you get an SO2,1 conformal algebra, of which the Hamiltonian is part. And sorry, is there a, yeah, it's a pen pointer here. What's the reason? The Laplacian is represented by the Hamiltonian in the usual way. The dilatation operator of this conformal quantum mechanics is a homothety. And the algebra is completed by the existence of the potential for the homothety, which is a harmonic potential on the manifold. And in this context, the problem of non-compactness is not serious in terms of our analysis, because we're really interested in the spectrum of the dilatation operator rather than thinking of the Hamiltonian in the traditional sense. And within the conformal group, the dilatation operator is isospectral to the combination H plus K. So we're really thinking about effectively a quantum mechanics with a harmonic potential on our target space. So as usual, we can ask what extra structure we get in the supersymmetric case. We can expect that to be more controllable and to have sectors which we can analyze exactly. And indeed, there is a series of nice generalizations of the basic bosonic quantum mechanics, which go up to a kind of maximally supersymmetric case, or maximally supersymmetric non-trivial case, which is the case where we choose as our target manifold a hyperkähler cone. So that means a geometry in which we have a homothetic killing vector, but it has to be holomorphic with respect to each of the complex structures of the hyperkähler manifold. In the context of supersymmetric quantum mechanics, our Hilbert space is going to be the space of forms. And one can show that if you have this tri-holomorphic homothety, the algebra that Strominger and Michelson found is enlarged to a very nice large superconformal algebra, which corresponds to the Lie superalgebra OSP 4*/4, which in addition to the conformal group that I described previously, it closes onto R symmetry factors which act on both the bosons and the fermions. And there are also interesting versions of this for Kähler manifolds and various other geometrical situations in which you get other Lie superalgebras appearing here as the superconformal algebra. So the idea here is that we're going to think about these sigma models and associate with them in the same way that we do with higher dimensional conformal field theories in radial quantization, a theory with a discrete spectrum. And the idea is that associated with these sigma models, there should be a discrete spectrum which consists of unitary irreducible representations of this superconformal algebra. And as we'll progress, I hope I'll show you that there's a certain amount of evidence accumulated, at least in some special cases, these theories do exist. Okay. So before we address the practicalities of dealing with the fact the manifold is singular and the fact that you have to regulate this construction, let's just suppose for a moment that we do have a spectrum of irreducible representations of this superconformal algebra. Then the structure is very similar to the ones that you meet in higher dimensional superconformal field theories. In particular, one can analyze the representation theory of this Lie superalgebra, and you discover that there's a classification of representations into short and long, with the short ones being distinguished by the fact that their Cartan generators saturate a BPS bound. So I introduce here some generators associated with the dilatations on the manifold and the different factors, which ultimately will be something related to angular momentum and R charge, which we'll call J, Q1, and Q2. And these all appear in the BPS manual. So short representations of superconformal symmetry are distinguished by the fact that they contain special states, not always the primaries, but either the primary or first excited state in the representation, which saturate this BPS bound. And as in higher dimensions, there's a construction which you can use to extract the content, at least up to alternating signs, of these representations by taking the appropriate trace, the superconformal index. So we can take a superconformal index, find a superconformal index associated with any spectrum of such representations by tracing with a -1 to the f. And as usual, we can grade the index. We can put inside the trace those generators which commute with the supercharge we use to define the index. So in general, there's a little group preserved by the BPS bound, and its Cartan generators correspond to the sets of charges which I've shown. And one can go a little bit further, as we're interested in actually counting the BPS states in our model. That will be the subject of interest. So what we'll really be interested in doing is actually extracting the information from this index by Taylor expanding it in powers of the variables, the fugacities, and extracting from it the integers in the expansion which encode the number of states that appear. And of course, because we're dealing with these unitary lowest weight representations, we'll get some finite coefficients here. In general, because we're taking an index, they will be can have either sign, but they can be thought of as coming from underlying degeneracies, which are traced over with an alternating sign in the usual way. So ultimately, we'll be interested in the problem of understanding these numbers in the models and extracting their asymptotics. That will be the problem that's tractable in these models. But as I've alluded to already, there's no free lunch here, and we have to face the fact that the models we're dealing with, and indeed this discussion in terms of an algebra acting on the Hilbert space of forms on the manifold, isn't well defined because the manifold itself is singular. So the natural thing to do is to regularize the singularity, to smooth it out, and at least for a nice class of these hyperkähler cones, particularly those which possess what's called a symplectic resolution, there's a very nice way of doing that. These manifolds occur in large numbers as Higgs branches of higher dimensional conformally invariant theories in 4 dimensions, for example. The Higgs branch will always have the form of a hyperkähler cone. And sometimes under suitable circumstances, it's what's called a symplectic resolution, which is a particularly nice resolution, which preserves a lot of the structure, although of course it breaks the conformal invariance. It preserves supersymmetry and enough of the global symmetries that we can continue to define the BPS states we're interested in. And the philosophy here is that we should think about this resolution as an ultraviolet cutoff in the same way that we do when we're defining quantum field theories, conformal field theories in higher dimensions, and that ultimately the theory we're interested in is actually defined in some sense by a limit as this regularization parameter goes to 0. But we'll be interested in BPS quantities which you can calculate, which are independent of this cutoff. So once you introduce this cutoff and smooth the manifold out, as I've said, if you have what's one of these nice resolutions called a symplectic equivariant resolution, then it has the property that the supercharges you use to define the superconformal index are preserved by the resolution. So although the superconformal invariance itself is gone, the BPS states which you're trying to count to compute the index are still there. And they're realized in the usual way in, now we have supersymmetric quantum mechanics with a particular potential on the manifold, and the states are realized in the usual way as the cohomology of a supercharge in supersymmetric quantum mechanics that with a potential that will correspond to the cohomology of a twisted Dolbeau operator on the manifold. And we also have the grading implicit in the definition of the index with respect to the R symmetries, which means that we'll be looking at the cohomology graded by the action of a group action on the target space, this resolved manifold. And you can count these states very straightforwardly just by localizing supersymmetric quantum mechanics with a potential. And one finds that the candidate superconformal index can be identified directly with a well-known, at least to some, invariant of the resolved space called the equivariant chi-y genus. So concretely, to compute the superconformal index of our singular cone, we resolve it and then compute the alternating weighted sum over the cohomologies, but it's graded by group actions, so we trace over each cohomology with the power. And the fact that this has to represent a superconformal index is already something that you can subject to various checks. For example, the structure of it being a superconformal index demands that it has an expansion in terms of representations of what I call the superconformal little group preserved by the index. And there are various checks that you can do that this identification indeed makes sense. So you can then employ the usual technology of localization to compute the index in closed form, as we have quantum mechanics with a potential, it's then straightforward to crank up the potential and localize the wave functions to fixed points of the group action. The usual story allows you to read off a formula for the index as a sum of contributions from each of the fixed points of the group action. So specifically, the classical index theory in this case tells you that you have to add up the fixed points, and there's a rational function of the fugacities which appears at each fixed point, and the data that you need to compute that is basically the character of the group action acting at that particular fixed point. So formulae that have appeared in various contexts in supersymmetric field theory in lots of ways. Okay, so this is something that we can compute this index. And now we want to, in fact, it's in the case that we're going to look at, it's a well-known object. But we're going to look at it from the point of view of superconformal invariance and extracting the degeneracy of states. So although we can consider lots of examples of hyperkähler cones, if we want a theory in which we can make immediate contact with a dual, then basically the class of conformal theories we're most interested in are conformal theories, quantum mechanics theories that come from underlying field theories via the mechanism of what's called discrete light cone quantization. So it's a famous old story from the 90s that if you take the interacting superconformal field theory in 6 dimensions with 2,0 supersymmetry, and you compactify it not in a space-like circle, but on a null circle, then the result is precisely a finite dimensional quantum mechanics. That indeed is the general feature of compactifying things on a null circle rather than a space-like circle. And Aharoni and collaborators famously conjectured, or argued, derived in some sense using string dualities, the fact that superconformal quantum mechanics on the moduli space of instantons is precisely the correct description for the sector with k units of momentum. And in terms of the conformal structure I described, that corresponds to the fact that this OSP 4*/4 superconformal symmetry that we found for a generic hyperkähler cone, in this case, actually corresponds to the light cone subgroup, light cone subalgebra of the 6-dimensional 2,0 superconformal algebra. When you consider fixing a light cone dimension, compactifying it, that breaks the superconformal group down to a residue, which is the group associated with a non-relativistic conformal field theory called the Schrödinger algebra. And the subalgebra, which is linearly realized in the sector of momentum k, is precisely the symmetry group of quantum mechanics on the instanton moduli space in the sense that I've described. So in this particular case, and I should say that there are variants of this construction that applies to apply to other field theories like n=4 super-Yang-Mills, and one can, there are variants of the story that I'm going to tell you, filled in less detail in some cases, which can be applied in those cases. But this is a particularly beneficial case, of course, because the instanton moduli space is studied in huge detail in the context of field theory. And indeed, the superconformal index turns out to be a very familiar object. It's, as I said, just the chi-y genus of the instanton moduli space. And the fixed point data is just the usual fixed point data used in computing the Nekrasov partition function. So we have the usual sum over colored partitions with a contribution from each fixed point being a rational function of the fugacities. But we also grade with respect to global symmetries in addition to the symmetries associated with the superconformal algebra in our context. And the generating function for, if we add up the different instanton numbers in the way that would be natural in the context of field theory, then the generating function that you get is indeed just the Nekrasov partition function for a particular 5-dimensional supersymmetric gauge theory, the n=2 star gauge theory. And this means that in this case, we can heavily exploit the setting, the fact that it's embedded naturally in gauge theory, to learn a lot more about the behavior of the numbers that I'm interested in calculating, the degeneracies of BPS states. So let's look at that briefly in the simplest possible example. which is the case of degenerate abelian instantons, if you like, where if you add the resolution in, famously associated with non-commutativity in the field theory context, then one gets a smooth moduli space, which is a resolution of the symmetric product, also described in terms of algebraic geometry as the Hilbert scheme of k points and c squared. Now, this is a particularly benign case because the generating function that we're interested in, which contains all the information about these BPS states, can be resummed exactly due to a formula due originally to Carlson, Nekrasov, and Akunkov. But this is a formula that's actually been proved rigorously using combinatorics by Rains and Warner. So one can actually rigorously add up the contributions from each instanton number and get this closed plathistic form. And more than that, it's even known that this expression, which involves the plathistic exponential, as it's got a rational function in its argument, that's going to be some infinite product. But it's actually an infinite product which converges to a known special function, or the elliptic double gamma function. So there's a lot known about this sum, and that's exactly what we want to exploit here to understand the numbers here that appear as the degeneracies of our BPS states. So this formula is very useful in terms of actually expanding and getting the information we want. One can use the resummation formula and expand it explicitly and actually look and see what the data is like for the numbers of these BPS states. It turns out to be very irregular at low instanton number, but if you go to, this is very much a small sample of the data if you like, but if you go to large instanton numbers around 50, then at that point patterns start setting in that you start to see that the numbers grow. First of all, they're definitely an index rather than just a pure count. As you can see, the signs alternate, and indeed the signs alternate in a way in which it's very hard to discern any pattern. But once you get to reasonably large instanton numbers, you see that the numbers start to grow uniformly. And it's an obvious question as to whether we can describe this growth in an analytic way. So again, there's a fairly obvious way to approach that, which is to copy the usual strategy for finding the asymptotics of combinatoric problems. So in this case, it's the combinatorics of fixed points. And that is to try and extract the coefficient as a contour integral. The coefficient we're interested in, the Taylor series, can be written as a contour integral of our generating function, imitating exactly the way that Hardy and Iliesiu computed the asymptotics of the number of partitions. So in order for this to work, we have to know enough about the analytic structure of the function z as a function of its fugacities, so z being the Nekrasov partition function. And certainly in the case of n equals 1, we can exploit that representation that I just showed you in terms of the plathistic and this double elliptic gamma function to actually understand the asymptotics of this function and its analytic properties in the complex Q-plane. And one can extract from that the behavior. You can find its singular behavior, and indeed it has an essential singularity, just like the original problem of Hardy and Ramanujan, near Q equals 1, and a similar point in for all the other fugacities. There's an essential singularity, and one can get at the asymptotics there from the modular behavior of this double elliptic gamma function. One finds that the integral has a pair of saddle points which approach very closely the contour as you take the limit, and I think it's fairly straightforward, and in fact it can be done with a reasonable degree of certainty, the evaluation by saddle point of the resulting integral. And in doing so, one finds asymptotics for that problem, which allow you to understand the growth of the numbers that I showed on the previous transparency. So in particular, in this case of n equals 1, or so-called abelian instantons, one gets a formula. As I said, it comes from two complex saddle points. So that means that rather than getting a single growth, we're going to get the contribution of those two saddle points will give an oscillating behavior. So indeed, this produces an oscillating sign for our coefficient. And there's an overall growth, which you can compute from the saddle point action. And one can check that indeed that reproduces, for example, the data that I showed you previously to about 1% in the exponent. So the asymptotic analysis really is capturing the dimensions of these spaces, which you can think about as graded subspaces of the cohomology of the instanton moduli space. One could do also a computation in the case of n greater than 1. Here you don't have so much concrete understanding of the analytic behavior of the Nekrasov partition function as a function of all its fugacities. But we do know from the physical setting that we must have S-duality. We know exactly how S-duality should work on the Nekrasov partition function. And there's a nice dual frame in terms of what are called M strings, in which the modular properties are more manifest. And you can use that representation, at least at large n, to extract an asymptotic also, which applies for the case of the large n instanton moduli space. So it's the exponent in the case where n is much larger than 1. Let me see how much time I've got
Is
left.
the degeneracy for large and fixed K?
Sorry?
This is the degeneracy for large and fixed K.
This is a degeneracy in which K also has to grow.
Okay,
So n is fixed and much larger than 1. K is growing, and L, which is the kind of conformal weight, is growing like square root K. There's a very particular limit involved in obtaining this. So I'm suppressing quite a few details here. And this should definitely be a tilde, not an equal. So this is the asymptotic growth that you get from the. We have not been able to test this, I should say, against. We can't actually expand the instanton partition function for SUN and reproduce this formula. It turned out that, well, basically because we don't have a closed plethistic form, we found it very hard to get enough data to actually check this formula. But we'll see that it does match something else, which is a holographic.
So SUN n equals 4 theory is partition function what theory?
It's the n equals 2 star 5-dimensional gauge theory. So the usual one which corresponds to the chi-y genus of the instanton. Okay, so I have a few minutes left.
Maybe a couple of minutes and 5 minutes for.
Okay, I'll have to be very quick. So this is part of a much larger story. So why should these things have a holographic dual? Well, the holographic dual is inherited from their relation to superconformal field theory, in particular the 2,0 theory. So one can actually obtain the superconformal quantum mechanics in some sense as a limit combined with an orbifold of the 2,0 theory to start with. One can take the 2,0 theory on a lens space, in fact, 5-dimensional analog of the lens space, and take a Penrose limit on that space, which is a limit in which you blow up the neighborhood of a null geodesic, and tune the orbifold in the same way, in such a way that you end up with precisely superconformal quantum mechanics. So this is something I don't have enough time. This is in our more recent paper. But there's a definite limit, and this was also studied, I should say, by Maldacena and Tachikawa et al. So one can obtain superconformal quantum mechanics from a very specific limit plus orbifold of a superconformal field theory. If you like, it's the conformal version of Seiberg's limit, in which you take a very large boost combined with a rescaling of the circle. And all one has to do is to take the existing correspondence to black holes in ADS and take the dual limit. So we're taking a kind of a Penrose limit on the boundary. And it turns out that in the literature on black holes in particular, the same limit was studied in the GR literature for many years and called the ultra spinning limit. It's a limit in which you take one of the angular momenta of the black hole to infinity while keeping the other ones fixed. And also you have to rescale the angular direction so that you get a finite solution of finite limits. So this is actually something that you can do to any black hole, not just in ADS, but we're interested in ADS here. This is a procedure which leads, it's a limit which in general leads to black holes with non-compact horizons. So the horizon stretches off to infinity, but the metric on the horizon is such that the area and therefore the Bekenstein-Hawking entropy remains finite. You can make these into geometries which are good in terms of M theory or string theory, because whether it was a null circle in the boundary description, that circle becomes space-like in the bulk. And at least near the horizon of the black hole, it can be made parametrically large so that supergravity is a good description. So to cut a long story short, one can take such a limit of the supersymmetric ADS7 black hole, which is characterized by 3 angular momenta and 2 charges. The state's saturated BPS bound, but only if a certain nonlinear constraint is obeyed. One can either take the ultraspinning limit first or the supersymmetric limit first from a generic black hole. Either way, you get the same configuration. You can compute its Bekenstein-Hawking entropy and check that indeed it does exactly match the formula for the asymptotic of the dimensions of the instanton cohomology that I presented in the previous transparencies. So I'm almost out of time, but this is really just part of a much larger story, as I've kind of hinted at. It's related to the notion of DLCQ and the fact that superconformal field theories can be regulated in DLCQ, or you can take a limit in which they're reduced to quantum mechanics. We believe that this could be a very useful scenario for studying black hole physics in general, because the ultraspinning black holes that you get seem to exhibit all of the phenomena, in particular, the analysis of things like entanglement entropy and the onset of signatures of chaos all seem to apply to ultraspinning black holes. But they really are dual to finite dimensional quantum mechanics, or at least a limit of that. So this seems to be potentially a very nice kind of arena in which perhaps some of the more physically interesting things associated with near BPS dynamics, like the SYK model, the onset of randomness and chaos, it might be possible to address and also maybe to make contact with numerical simulations. Okay, thank you.
Thank you. Okay, question, comments? Okay, okay, go ahead.
Same story generalizes to
Well, yes, the ultraspinning story is something you can do with any ADS black hole. So you could do this with ADS5 black
Well, it
holes.
has to be ADS.
Sorry?
It has to be ADS, cannot be.
I believe there are ultraspinning limits for asymptotic flat black holes. If you don't know, I don't have anything to say about them, so they're not holographic, so at least that I know of.
And sorry, another question. So you mentioned BFSS. I didn't quite understand what sense is BFSS a finite dimensional.
BFSS is a quantum mechanics of n by n matrices. It has a regime of parameters in which it's dual to a black hole background in 2A string theory.
Okay, so because the Hilbert space, it has the continuum. So
in this context, well, in this context, the Hilbert space is discrete that I'm interested in because I'm working with radio implementation. I agree in that case, you're talking about, yes, the Hilbert space has a continuum, but it's still finite dimensional, right? In the sense it's a finite dimensional. The field theory, the matrix model, has a finite number of degrees of freedom. So that's the distinction I'm making. But in this case, it's actually a discrete spectrum within a finite dimensional model that we're looking at.
Okay, let's thank this people again. Now we have a coffee break, 30 minutes. Before that, I have a question. I see there are some local postdocs and grad students here. If any of you plans a hike or whatever, something like this in the countryside, maybe on the St. Croix River, please let me know, because some participants of this conference who stay here beyond Saturday, Sunday, would like to go to the countryside. But this is, of course, if somebody plans. Okay, the second quick point that after the dinner, today conference dinner, I will show some pictures which I had made 22 years ago, and it is funny to look at people. What 22 years have been. Okay.
Hearing?
That's right.
Spindles are.
Yeah.
So we, you know, I think you might be able to get an ultra spindle from a spindle. Yes, it seems to be we've been specifically looking at all folds without physics. If you have a 3-sphere or a 5-sphere,
and those are saying that's what you have to do. Yes. So I think yes, so one of the angular momentum to infinity was scaling with a whole number, so that the direction along the hot fiber is also going to be you end up kind of boosting in that direction, but at the same time so it's independent on the it keeps it still, but it's certainly becoming so a story where you have a compact circuit, you go to you know, you can form a direct boost in that direction, and will have the effect of depending on the reference from band and shrink circuit. So it's just kind of it's a combined boost. Keeps the hot circuit and not one kind of
Yeah, I just wanted to make sure that I can use this one. Thank you. Very much.
Yes, so when you give your presentation, you'll go through it with this one, not with this red one.
Yeah, I need to use this one because I also need to use this.
Okay,
Yes.
we can find another adapter because this is what's running our Zoom, which is running.
You have another one also.
Yes.
Afternoon. Thank you. This will be very helpful because I forgot to bring this from home, so I was wondering because I should run to the bookstore. If you have already one with the guy who went to Denver recently. Very helpful. Thank you. Marcus Greiner?
Yeah, Greiner.
Yeah.
Yeah. Maybe it's hard to say if it's a tendency because these are very small numbers.
Yeah.
Of the fluctuation.
I mean, one could say that in Europe there was for a long time there was a decreasing in the number of positions probably, and now it's getting and so probably that's attracting.
Thank you very much for the kind invitation. Fortunately, I don't have much to say about supersymmetry today. I hope it's acceptable.
yeah, my slides have like one word about supersymmetry about how like this could be done in supersymmetry.
Yeah, I see. Oh, good. I'm very glad to hear that. Yeah.
You're not the only
Very good. I have 4 words, four supersymmetry in my
In the
one.
second talk, the Hamiltonian at the end, it has a continuous spectrum. It's just that these BPS states are some special ones.
Yeah.
So how can you hope to make contact with? Oh, maybe for this highly spinning black holes also there is no gap for non-BPS. Okay.
Yeah, maybe.
Yeah, anyway, we were just talking that Europe seems now more attractive. In Storybook, we had a surge this year. And the
I know.
majority of people that we wanted them to apply said that they're not gonna stay in the US.
Why?
I don't know, they just want to move to Europe. They got jobs in Europe. Better life quality.
Really?
Yeah.
That's very interesting.
So this year, the European job market was significantly stronger than the US
Yes,
job market.
European, no, but the best people in
You mean in terms of faculty or postdoc?
Faculty.
Faculty.
the best people are going to Europe the last couple of years, I would say.
Really? Example?
Well, the first one was Sasha Shibuyedov.
Okay.
Now it's Lorenz Eberhardt.
Okay.
Yeah, he went to Amsterdam.
Yes.
Yes.
think it's still confidential. I shouldn't say that, but IGS made an offer to somebody who hoped would apply.
Yeah.
What's his name?
Yeah, Julio.
Julio Paramartinez.
My colleague.
Julio Paramartinez.
Until
Oh,
this time.
interesting. He's
Yeah.
going to IGS?
No, not clear.
I don't know if they already made the offer or not. It's still.
I see. He has the other
Yeah, he already accepted
something.
to go
UBC
to
or
go to
UBC?
UBC. Yeah.
It doesn't matter. They'll forgive him once.
Yeah.
They won't forgive for the second time, but you can do it once. So I see, maybe it's not a trend, maybe it's just a fluctuation,
I don't know.
but I see that.
But I think one point was just that there were many more opportunities in the last couple of years in Europe.
There are openings. There's an opening in Berkeley, Stony Brook. I think there's a
Here.
there's a yeah, there's a search here.
There's not a junior research here though.
I don't know. I think there are openings, but they don't even apply. There was an opening in Chicago. They don't even, as you know, they don't even apply some weeks.
Yeah.
Anyway, I was just saying, he was saying that Paris, the community is growing and it's getting better. So I'm saying that.
But it's good that there are positions. I mean, it's better than not having positions.
Yes.
It's a good sign that there are more positions than the number of people you might.
Yeah, actually, I would say so, yes.
Yeah, I think it's a good.
I would say it's difficult to find a good match. There are more positions.
That is possible.
What are you going to talk about today?
I was planning to talk about the charge fractionalization monopole polymer thing from last summer, since it has something to do with being on a moduli space and that kind of logic, but I don't have to talk about
Maybe you don't have to give you prefer slide.
that. I have some slides, but I have slides on other docs too.
Another.
No, so you haven't.
So you can use different.
Yeah.
Maybe you can use that. You can give menu and then people can vote.
We'll do a prefix.
Prefix? No, but
All the talks.
I don't know, Zohar, I mean, do you want me to talk about that or do you want me to talk about something else?
Yeah, I'm not the boss here. I just help Misha identify young people.
That was hilarious that Thomas Strongarm being becoming a representative. Sorry, I can't come.
Seen how loud it is,
Oh, yeah.
the drilling, yeah. Where to go out here? Oh. Yeah, that's good.
Well, people can start using the microphones.
Huh?
People can start using the microphones.
Oh, yeah.
So then they'll be able to hear pretty well.
Oh, that's good. It'll, yeah.
Speaking of talk, going on this, adding a couple of things, just adding a couple of things. Yeah, I feel the same thing. You have to kind of, bring the crowd. Yeah, so that's one. Anyway, I'll do it. That's fine. But you mean the US? Okay. Well, no, for a while, yeah, I did the summer.
Hi, Alicia, I think
I mean, I'm here.
maybe because they are not going to stop right now.
They're not going to stop ever.
Okay, I'll go up to the floor. Huh?
You can hear it up there.
Well,
It's
You were
not,
there?
yeah.
So it doesn't save us.
No, this building echoes too much. But we do have microphones.
Okay.
I see.
So if people use the microphone, it should be loud enough.
Yeah, but it's very upsetting. A lot about the third floor, the seminar room on the first floor.
I don't think it's available, but we
Not
can take a
available.
look. We can see if somebody's willing to move. Or I can ask Earth Sciences if.
Like some slight- I was thinking on this one. I mean. The weakness is that it's too similar to condensed. To condensed matter, like, you know. The infinite order, large quantum number stuff
is condensed matter, right? It's just whatever, the ground state of finite density. It's all the sort of the structure on top of that, which is somehow, I mean, we are definitely interested in experimental applications of condensed matter because there are situations where people consider finite numbers of atoms, these like cold atom systems, so like boson, it's finite atomic number, finite atom number of corrections to those are really interesting. Experimentally and theoretically. And we are definitely thinking about those. I mean, we've been trying to work out these like edge effects, these edge corrections to harmonic trapping for a couple of years now. I see. That's mostly what we've actually been working on. But for high energy theorists don't want to hear about it. That's true. That's true. They want so we mostly emphasize the differences from that sort of reason. But one of us is important. So yeah, it's important. But yeah, well that's true. That's true. But depending on I mostly talk to high energy audiences at the moment. So yeah, for this audience, it's gonna be a lot.
Yeah, that's clear. That's very clear. All right, I'd like to move to that side because the speaker is always on that side.
Okay. Time to start. After the first coffee break. Next, we're going to see Argyres, University of Cincinnati. University of Cincinnati. The title of his talk, the extended vertex algebra in four-dimensional n equal to SCFTs.
Okay. Right, I'm gonna talk about some, first of all, thanks for inviting me. It's nice to be here. It's been some years. I'm gonna talk about some work with Weaver, my student, and on an extension of the vertex operator algebras of 4D equals to superconformal field theories. So you see that the basic idea probably can be something more generally than in this class, superconformal. And the basic question what motivates this is that, first of all, given that there is this this large protected subsector of superconformal field theories, this vertex operator algebra, I'll remind you what that is in a minute, made out of local operators. A natural question is whether there is an analogous structure for extended operators, line operators, surface operators, wall, domain wall operators. So let me remind you, first of all, what this vertex operator algebra is. What is a vertex operator algebra? It's basically the chiral half of a two-dimensional conformal field theory. So it has a bunch of operators that you can put on say a complex plane. Let's give it complex coordinate Z, and then the operators only depend holomorphically on Z, or their correlators are mirromorphic. No branch cuts. And furthermore, there is a conserved stress tensor, which acts like a Virasoro operator. And if you had the same structure with a few extra, some certain properties, but no stress tensor, it's just called a vertex algebra. So a vertex operator algebra is maybe better called a conformal vertex algebra. It's good to keep in mind the distinction, as we'll see. And the point is that it's shown famously 10 years ago by these authors that every unitary four-dimensional n equals 2 superconformal field theory has a vertex operator algebra. That is to say, a subsector of its local operators, which form a vertex operator algebra. And this gives you a lot of information about the superconformal field theories. So let's see how this comes about. This two-dimensional plane is just embedded as a spatial plane. Let's put it in the x3, x4 plane, with x1 being time and x2 being another spatial direction perpendicular to the plane, and we'll just put complex coordinates on that plane. That will be the z plane. I'll call that the VLA plane for this vertex operator algebra. And the idea is we simply insert a special local operators from the four-dimensional conformal field theory on this plane and take their correlation functions, and they have these properties. Well, what operators do we insert? Well, you look at operators which are BPS in a certain thing. They are annihilated by a certain nilpotent supercharge in the superconformal algebra. I'll call it T, actually T plus, because they'll turn out to be two supercharges that play a role. T for twisted shore. A local operator which is annihilated by T plus is called the twisted shore operator. At the origin, those are the same as the shore operators. And then that's all you need to know. You stick them in correlation functions. They have those properties of a vertex operator. So it forms this huge, infinite algebra of this protected subsector of the operator algebra of this superconformal field. And it's a property of these unitary superconformal field theories that they all have an infinite number of these shore operators in respect.
Good. So the field theory doesn't know about the plane you inserted, or doesn't?
The choice of that nilpotent supercharge T is what picks out that plane. Of course.
Including the positional plane? So can I have two planes parallel to each other?
Great question. It turns out it picks out the position of the plane as well. In some sense, if I just chose one of these supercharges, T plus, it doesn't care about the position. But as soon as I pick the second one, it picks it out. And it's important. It's not important so much for the VOA story that you pick both, but it's important for our story that you pick both. So of course, I'll give you a specific supercharge, tell you what this supercharge T is later. But of course, I could have conjugated that supercharge by anything in the formal algebra. That would have been an equivalent supercharge. So I could have clearly rotated that plane as I like. So the fact that it's the X3, X4 plane is really that special. So let me go back to my motivation. Here are the questions then, the natural questions in this context. What extended operators are in the cohomology, are annihilated by this particular supercharge? And if I can find them, is their operator product integral? And the answers, this is what I want to tell you about, is that there's a very natural way of extending, constructing extended operators annihilated by T. It's an analog of the topological descent procedure introduced a long time ago by Witten in the context of topological field theories, where you are also looking at operators in the cohomology of a nilpotent supercharge. And if you had a local operator, that topological descent allowed you to then construct line, surface, and whatever operators. We're going to just going to borrow that essentially. We're not in a topological context, but that doesn't matter algebraically. We do the same thing. So for every twisted shore operator, there's an associated class of descent operators, which are lines, surfaces, and domain walls. And these things then automatically form a vertex algebra. Maybe not a vertex operator algebra. The jury's still out on that. So here I'm just going to summarize the results before I give you any details. So this is just what I said. The descent procedure takes for every shore operator, it gives us a whole associated class of extended operators. Those extended operators are much more rigid than topological operators. They lie on very specific subspaces here. So X3, X4 axis here, that's the whole VOA plane. I don't have enough dimensions, but if I started with a shore operator at the origin and I did a descent procedure on it, I can get a line operator out of it. It is a light-like line in this particular direction going through the origin. And there's another related descent procedure, which gives the other light-like line in that TX2 plane. Or I can continue with either of those guys and do a descent again, and I can get a surface operator filling
the Tx2 plane. And it doesn't, those are, I'll just talk about those for the moment, but it doesn't stop there. There's a different surface operator, which gives a two-dimensional slice of the three-dimensional light cone going through the origin, and they're wall operators. But let me just stick with these three. I put them all at the origin, but they didn't have to, they could come from descent through any Schur operator, any place anywhere along the VOA plane, the X3, X4 plane, in which case you just kind of translate them like that. So here's a configuration of them. And then you can take their correlation function, and they are meromorphic functions only of their kind of intersection, the holomorphic coordinate of where they intersect the VOA. So from the 2D point of view, from these set of correlation functions just look like the correlation functions of the chiral half of the two-dimensional theory. So that's a vertex, and they satisfy the rules of a vertex algebra. So this is what we found. And the question is, well, now we're exploring this structure. We want to understand.
What is the distinction you are making between vertex operator algebra and vertex algebra?
Yeah, the vertex operator algebra is the name for a vertex algebra, which in addition has an operator which organizes the vertex operators into irresolvable primaries and descendants. This does not have to be the case.
There's always another geometry.
In the 4D theory, no, but that doesn't tell you that it is in this effective 2D. So for example, in the Schur operator, the local operator sector, you do get a vertex operator algebra. And Beam and company famously located it. It wasn't the stress energy. The thing that played the role of T in the vertex operator algebra is not a Schur operator, is not the stress energy operator. That's actually not a Schur operator. It turns out to be an R symmetry, a certain component of the R symmetry. That exists for the vertex operator algebra. Let me get to the. I will make sure I get to the end. Well, I'll actually compute in an example, free hypermultiplet theory. You'll see how things go wrong.
If I'm just trying to, but in 2D it would be local operator, right? Or
yeah, all these operators look like local operators in 2D.
For 2 dimensions.
2D, even though they come from these extended operators in 4D.
Are there generalization to extended operators in 2D? Like, can you have an extended operator also?
It's an interesting question. Yeah, the operators that I'm kind of leaving out, the wall operators, for instance, that I talked about, they actually act like line operators in a certain sense in 2D. So yeah.
I don't know much about this, but normally when I do the operator algebra in formal algebra, I take the integral of Z, the operator, use the operator product expansion. Is that the type of thing you're going to do?
Yeah. So that's the typical operators you get from this descent procedure. I'll review that in just a second. So they're not like these operators that these extended operators don't look like Wilson line or multiply, exponentials of integrals of local insertions. Instead, they're just more additive, right? So they kind of get additive renormalizations instead of multiplicative. Still exist, still have interesting fun. Okay, so in the time remaining, I'll do this I'll go through both the introduction of the twisted Schur operators and the descent procedure in a little bit more detail, so you get a little bit more details about what's happening. And then I will go and give you the results of doing a specific computation of the operator products expansion of some of these extended operators in the free hypermultiplet superconformal. So here's the superconformal algebra. Conformal algebra here, dilatation, special conformal transformations, and the R-symmetry algebra, and the 16 supercharges, the regular supercharges and the conformal supercharges, and the nilpotent operator that we're interested in is a certain nilpotent combination of the Q's and the S's. I'll take for my definition of Q plus these particular components of Q and S. There's two indices because there's an R, because it's an N equals 2 theory. So there's an R symmetry index on the Q's as well. Okay, so you usually check it's nilpotent, and the twisted Shor operators are any operator annihilated by this supercharge. So they're annihilated by a supercharge, so they are BPS operators. So if they're annihilated by just this one supercharge, I guess you would call them 1/16th BPS operators, but they're actually in unitary theories automatically annihilated by a second supercharge. So they're really 1 BPS operators in general, but they're all
calculated means just the product or commutator.
Oh yeah, sorry. Yeah, this is my notation. The little circle means commutator. Yeah, or
yeah.
The Lie bracket, the super Lie bracket, right? I just got tired of writing. And of course, it's not just the local operators, but you can ask about the elements of the algebra itself, whether they are annihilated or they are exact. That is to say, a generator X that's annihilated by T plus might be exact. That is to say, it might be T plus of some other fermionic generator. I'll take X to be bosonic. And then these X play a special role just from the T plus word identities of correlators. They generate the symmetries of correlation functions of these Shor operators. And this will apply just as well to the extended operators. So the T exact things, for instance, look, there's this L-1, which involves translations in the anti-holomorphic directions in the VOA plane. And the fact that this is an exact generator tells you that my correlation functions are independent of the Z-bar coordinate. And the T exact ones are, of course, closed. The ones that are closed but not exact, all of the closed ones will take, when acting on an operator in cohomology, I can use them to generate, by exponentiating their action, to translate or generate a new operator in the cohomology. And so, for instance, the real combinations of this L hat minus 1 and this L1 allow me to move my operators in this ZZ bar plane as I like, but because these guys are exact, it tells me that the correlation functions of those operators are independent. So that's the basic idea of how going to the cohomology of a certain nilpotent operator, but just the word identities for these BPS operators will give rise to this vertex operator, vertex algebra structure. It's not at all obvious from this why it's a vertex operator algebra. That's kind of, it's just not obvious. Now let me remind you about the descent procedure. If I have an operator, let me write it as kind of an inductive sort of thing. If I happen to have an extended operator of world volume dimension n that's annihilated by T plus, then there's a procedure called the descent procedure for generating an extended operator of one larger world volume dimension that is T closed. And the idea is I choose one of these T exact generators, one of these kind of symmetries of the theory. It is, because it's exact, it's T plus of some fermionic generator. And then I take my extended operator and I I translate it by this this exact operator. In other words, I just take its action of this generator on this operator, exponentiate it, and I integrate over it. So let's say the EN operator was one of my light-like lines, and this X operator is a translation in a perpendicular direction. Then integrating over it would just translate that line and sweep out a surface. And so I would get a new operator, which would be a surface operator. And then you can show that it solved it is itself T-closed if you don't take this T-closed operator, but you take one of its super descendants in particular by this fermionic operator. So if you started with a bosonic local operator, then you would get a fermionic line operator. And if you did it again, you'd get a bosonic surface operator and so forth. This is the same as the structure that you found in topological that introduced by Witten in topological field theories back a long time ago, 35 years ago. This isn't a topological theory, so all we can do is integrate these guys. If these guys are translations, well, it turns out in all the interesting cases, in our case, this parameter that we integrate over isn't a compact parameter. It's the real line, and there are boundary terms, and you have to worry about the boundary terms in convergence, and that's the delicate part of this whole construction that we have. The part that we spent.
By boundary term in alpha integral?
Yes, boundary terms in the alpha integral. So I gave you this light-like line operator. It goes off to scribe plus or minus. You have to worry about the convergence, what that does when you insert those in correlators. So
Because naively it doesn't exist if you apply the operator you started.
I'm sorry, what?
Naively, if you apply T plus to your descent, it returns back En. What you write is like a shrink representation for a propagator, 1/x. And then you apply Q.
Right, it's slightly more complicated than that, but more or less, the
becomes total derivative.
It becomes a total derivative, and so it gives you a boundary term, which is the operator, the original operator itself out at that boundary, and you will have to make sure that those boundary contributions are convergent or don't give rise to divergences in the correlators. That delicate part is by far the thing that we spent the most time working on, but I'm not going to talk about it. I'll happy to be talking about the details later. I'm not doing it. Okay, so I'll go through this pretty quickly. Here's an example. Let's look at the T-exact generators, which move the origin. Well, the T-exact generators, T plus exact generators, was this set of generators. They include a translation generator, which moves the origin, plus a certain set of Lorentz guys and a special conformal, but these guys don't move the origin. And to get an extended operator, or actually a convergent operator, I need to move the origin. So I only have one choice, which is to do descent with respect to the P plus operator. And if I do that, I get this L plus line operator. Okay. And so my VOA or my short operators plus these L plus line operators would then form some vertex algebra. And once I have this line, I can ask, can I do a T plus descent on this again? But it turns out none of these operators move the L plus line. So if my descent stops there. If I try to do this descent procedure, I would formally get something that's D plus closed, but it's actually a divergent object. So that's pretty boring. Just we got a line and that was it.
But construction is tied to Lorentz signature.
Oh, and this, yeah, thank you. Important point. This only worked in Lorentzian signature because it gives a light-like line. If you try to do this in Euclidean signature, you would find no. You wouldn't be able to do the first step of the descent. But this is not the end. They're basically due to unitarity that the the twisted Shor operators, which are in T plus cohomology, are automatically also in T minus cohomology for another nilpotent supercharge. The first one was made out of Q and S twiddle. This one's made out of S and Q twiddle or something like that. These notice, by the way, T plus and T minus are nilpotent, but T plus commutator with T minus is not zero. They're not anti-commuting supercharges. And so I could just as well try to do topological descent with the T minus operator acting on the Shor charges. And it turns out that the T minus exact generators are not the same as the T plus exact generators. In fact, they're the same set I wrote before, but with minus signs. So if I acted on the Shor operator with T minus descent, I would get a line operator in T minus cohomology, but which would be along this L minus line as opposed to the L plus line.
Doesn't, why is that? You know, before you did extension, it was like kind of analytic particle sense, like degeneracy at this point, because there's this difference of algebra will tell you that at the same point you say it Q, but I'm trying to say that it's like still degenerate. There are two, not one. This vertex operator in certain sense.
It's not so much that it's the vertex operators degenerate. It just happened to be from the vertex operator algebra point of view. It happens to be in these.
I'm not sure
in both of these cohomologies. And now I could choose either one to make descent operators. And you would naively, you would say, oh, well, one is a vertex algebra, now an extended vertex algebra relative to the T minus cohomology, and the other one is the T plus. But there's this happy accident that the extended operators, which we find in, say, we construct by descent in T plus cohomology, are automatically in T minus cohomology. And I call it an accident because unlike the reason that the twisted Shors were in both had a nice understanding in terms of the structure of the superconformal algebra and unitarity of the field theory. And we don't have an analogous argument for this. We can prove it, but it just follows by some some sort of delicate algebraic relations among the superconformal generators and not some nice thing having to do with some sort of automorphism of the superconformal algebra that we can. So this is kind of a central mystery of what we're doing, but it's a very happy accident. And it allows us to now just do arbitrary T plus and T minus descent and build up a much larger set. So if you just keep on doing that, I'm going to skip ahead. Then if you start with your Shor operator, you can go do P plus, P minus to get L plus minus. You can do P minus and P plus again, either they close on the same thing, a surface operator. And those are the ones that I kind of mentioned at the introduction, but you can also do, there's many more, and you get this whole tree of other surface and wall operators. There may be some identifications among these 8 different wall operators. Anyway, we're working on it. So the wall. Okay. So I wanted to jump ahead to the.
What is the anti-commutator of T plus with T minus? What do the anti-commutator?
It's the thing that that the Beam company called the central charge. It's Z, which is a certain linear combination of the U1R charge and I guess the Lorentz generator, which we call M plus minus.
It includes rotation of space-time.
What's that?
Does it include rotation of space-time?
It includes a certain
boost. It's a boost.
Yeah.
What's the Lorentz boost?
I hope I'm getting this right. So I wanted to give you an example of, of course, we went to a free field theory to compute. The computations still turn out to be quite complicated, unfortunately. but let me just try to give you the answer. So I have to pick a bunch of short primaries in the free hypermultiplet superconformal field theory. There's one which is the actual scalar superprimary. This particular two components of it are Shor operators or twisted Shor operators. And there's a certain component of, and then this actually strongly generates the entire vertex operator algebra, one of local operators. And there's another one which is the Virasoro generator in the VOA, which is a certain component, which I've written here, of the SU2R current. So let me just look at descent procedure where L plus, L minus, and that surface operator built on these two shores and their operator products. And I know I'm going to flash for you the structure. And here there's something going here. This is more or less telling you that they have this. They have the structure that their operator products of the ones built on this this low dimension Q operator. They look like these. They all have the form as their singular pieces in the OPE close on a constant over Z. So they close on the identity. And all that we have to then, once you understand that, all you have to do is compute that constant. We can do that, and here's the and here's the one that I really wanted to spend a second on. I can look at the descent operators coming from the Virasoro operator and of these other operators Q, and we see, of course, and they all look like they have a form that's very reminiscent of the Virasoro algebra. T on an operator Y has the same structure as acting on an operator Y. This 1/2 is because all of these Q operators in this case have this kind of conformal dimension 1/2 in the VOA. And indeed, T on Q closes on Q, just as you expect. It is, after all, plays the role in the vertex operator algebra of the Virasoro generator. But you see T on S, even though this is a surface operator in spacetime, it actually, in cohomology, closes on a local operator on the right-hand side here. And this is not the action of the Virasoro generator. So maybe you say, oh, well, maybe I'm just not, I have to diagonalize my basis between Q and S of Q in order to diagonalize this action. But it's impossible to do that. It can't be diagonalized. T, at least in this very small subsector of the algebra, does not act as the Virasoro. It's a Virasoro operator in just the VOA subsector, the local operator subsector, but it does not act as a Virasoro generator.
So your
full vertex
expansion, it's in 2 dimensions, right?
Still, well, yeah, two dimensions effectively, just just the holomorphic pattern.
Yeah.
Right. But the question is there an operator that acts on everything, all of these things, which look like local operators of dimensions, that acts like the Virasoro generator? And we can't find any in this small set, but this is far from ruling it out because there are many appropriate kind of conformal weight 2 operators that we can write even in the free hyper field theory. And then you can also ask, what does the TP type OPEs, and I'll just leave that up there. No, maybe I won't. Maybe I'll just flash to the outlook, which is we really need to understand much better the algebraic structure of this vertex algebra that we found. The next steps, we've done it for the free hyper, let's compute it for the free vector. We've actually mostly done that already. And this, if you have the 2 of them, then you can start using perturbation theory, doing computations in weakly coupled conformal gauge theories. And then the other thing is you can construct Wilson and Tuft-like, as opposed to these additive like line operators in T plus minus cohomology. people often said that they don't exist, but that's because they were working in Euclidean signature. They definitely do exist. They are light-like again. And try to understand them as both as modules of the vertex operator algebra and of our descent vertex algebra. Those seem to be the easy next steps.
Okay, thank you. I think we have maybe a couple of minutes.
So, so could I understand correctly that the vertex algebra, which you computed for the free Hypermall spread, corresponds to that with symplectic modules?
The vertex operator algebra, that's true. We don't know what our vertex algebra. No idea. We don't even know what a generating set that vertex.
So there are more operators than just.
Yeah, here.
Symplectic modules are just being a Bethe-Gauss system with.
Yeah, I understand, but if you look, here is our list of the Virasoro guy and if you just look at the structure of the OPEs, among the singular terms, you get many new objects, which are normal order products, that they're no longer descent operators anymore. Should have mentioned, by the way, that these light-like descent operators are very reminiscent of what are called light ray transforms that have been introduced in the conformal field theory literature by Kravchuk and Simeon-Stuffin a while ago. And just as light ray transform OPEs don't necessarily close on light ray transforms, they close on a more general set of light ray operators. There's a similar thing going on here. So
also fermionic operators.
Yeah. In these cases, the lines are fermionic and the surface. They all have the same kind of conformal.
So if you had if you just took the action of the free hypermultiple in four dimensions and tried to write it as a T plus exact plus something which is T plus closed, could you just identify what you get? Because that's what you usually do. If you have a nilpotent supercharge, you try to throw away all the garbage. Look at the essence of the theory.
The question is, how do I? Here you're taking the 4D action in doing this, but I don't know how to extend that.
Because you have extended operators.
Anyway, it's interesting.
When you are having this extended operators, before this vertex operator in 2D was like a local operator, right? This extended operator, what would be their projection to 2D?
Just a point. So that's a puzzle. That's a
puzzle. They still
local, right?
They're still local from the 2D point of view.
Yeah.
At least the operators.
Yeah. So the fact that they come from extension does not show up in 2D.
In 2D, that's the puzzle. That's the challenge.
Okay, I suggest we stop here, and you can always speak during breaks, before dinner, at the dinner, after. And now we have to go to the next speaker.
We should thank Philip again.
We go to the next speaker, Luca Iliesiu from Stanford University, black hole microstate counting from the gravitational path.
Thank you very much for the invitation. So today I'll be telling you about how to count black hole microstates by using the gravitational path integral And this is work that I've done together in collaboration with Joaquin Turiachi and Samir Murthy, but I'll mostly focus on some work in progress with Jan Boruch and Cynthia Yan, who are both amazing graduate students.
You can't use this one.
Okay. All good?
Yeah, I got to get the Zoom back up and running.
Okay. Okay, great. So in the past couple of years, we've made a tremendous amount of progress in understanding how the gravitational path integral for a variety of black hole observables reproduces features of conventional quantum mechanical systems. So this is one of the most important dualities. An example of this is just the SCFT, but we think it applies at a broader level. And this is what we would like to test in more detail. So today, I shall review some of the progress that we made towards understanding this equivalence for supersymmetric black holes. So there are two ways in which we can understand this duality. The first is through the Gibbons-Hawking prescription, in which one assumes that by studying gravitational solutions that have a periodic time with period beta, we're actually computing the partition function of the quantum system that's dual to a black hole with inverse temperature beta. So in the first part of the talk, I will talk about what this tells us for BPS black holes in the limit in which we take beta to infinity and fix the charges of the black holes. Nevertheless, this prescription on the left has a problem, which is that it is unclear why it works, why it actually computes a partition function. So in contrast to conventional statistical mechanical systems, where in order to compute a partition function, we make the time circle periodic, there the time circle is non-contractible, and it's clear why the partition function actually computes a trace over states. In all the black hole examples that we know of, either the time circle or some linear combination of the time circle and another space-time direction is always contractible. And therefore, it's actually unclear why this prescription actually computes a trace over a Hilbert space or why it computes a partition function. This brings me to the second way of understanding the duality between black holes and conventional quantum systems, which is by using string theory. So as we know, Strominger and Vafa accounted for the extremal black hole entropy by computing a string theory index and weak coupling. However, even this method has two problems. The first is that it's actually computing an index instead of a degeneracy, and it's sometimes unclear why the index and degeneracy are the same. And the second is that it's a computation at weak coupling. So even if we construct the states at weak couplings, it's unclear what that means for the gravitational states that we're actually studying. So in the second part of the talk, I will explain how to construct a complete basis of states by using the gravitational path integral instead of string theory. And these states will have a very clear geometric meaning. So the part one will be very quick. So please ask me, it will just be a flash review. So please ask me more questions after the talk if needed. So I'll talk about an extreme version of the Gibbons-Hawking prescription, which is what happens as we take the temperature to 0 and fix the charges. So first, let me describe what kind of geometries we're studying in the Gibbons-Hawking prescription when we take the temperature to 0. As we take the temperature to 0, the black holes that we're studying become what are called extremal. These black holes have a very long stroke, meaning that the proper distance that an observer has to travel to the horizon of the black hole becomes very long. And the space-time close to the horizon of the black hole becomes a direct product of two spaces, an internal sphere, and two-dimensional hyperbolic space. For instance, if we're studying black holes in 4 dimensions, but this also applies for black holes in other dimensions, in other space-time dimensions as well. The advantage of studying this limit is that analyzing fluctuations of the space-times is actually a lot easier than analyzing fluctuations more broadly. But before we talk about fluctuations around these geometries, I just want to mention that the gravitational path integral at the saddle point gives an on-shell action that's exactly equal to the area of these extremal black holes in units of g Newton. which, for example, for black holes in flat space that have some charge Q is just e to the pi q squared. So where Q is the charge of the black hole, and if we want to study a macroscopic black hole, we should take Q very large. So in this context, if we want to understand the partition function more accurately, we should also compute one loop fluctuations around the saddle point. And there are two types of fluctuations that one can analyze. For instance, if one analyzes, let's say, the fluctuations of a scalar field on this background, it turns out that fluctuations of those fields at quadratic order are suppressed in 1 over the entropy of the black hole. So they're very small. And this applies not only to a scalar, it applies to a variety of modes, most modes of the graviton, gravitino, and whatever fields I have in my gravitational theory that I'm studying. But there's a small exception, which is that there are specific fluctuations of the metric and of the gravitino, if I'm studying black holes in supergravity, that actually have fluctuations that don't scale like 1 over the entropy of the black hole. They instead scale like 1 over the temperature. So these fluctuations were missed in the past. And the important thing is that they can become extremely large as we take the temperature to go to 0. The typical size of the fluctuation becomes very, very large. As Francesco alluded to, these earlier this morning, these fluctuations come from what's called the universal super-Schwarzschild mode. It can be viewed as the set of large superdifeomorphisms in the large superdifeomorphism fluctuations in the near horizon geometry of the black hole. So what do you get for the density of states or spectrum of these black holes if you include these fluctuations? So here is a plot of the density of states as a function of energy. First, let's focus on the red line, which is what happens if you only keep the leading saddle point. So this is the semi-classical density of states that was initially obtained by Gibbons and Hawking. So as you can see, it's a smooth line that goes to 0, and nothing funny happens as we approach extremality. This point, the reference of the plot, the reference point of the plot is when the black hole is extremal. However, if we include these large quantum fluctuations that occur as the temperature or as the energy approaches extremality, as the temperature becomes small, one can see that the actual density of states starts deviating a lot from the thing that Hawking and Gibbons computed. To the point where we see that the spectrum has an actual gap. So this is quite fantastic because from a gravitational path integral, we have managed to isolate a discrete set of states. These are actually the BPS black hole states that occur in supergravity, and they can be viewed as the first genuine signature of a Hilbert space for BPS black holes that can be solely obtained from the gravitational path integral. And the degeneracy of these BPS states, if we include the only quadratic fluctuations, receives a one-loop correction that goes like area divided by 14 newtons, so the entropy of the black hole, to some power. Can we do more? It turns out that we can. It turns out that we can classify all the geometries that contribute to this delta function that occurs at the extremal energy. Namely, for black holes in 1/8 BPS black holes in N equal A supergravity, sorry for the typo, in 4D flat space, we can actually compute this degeneracy exactly by using supersymmetric localization for the supergravity path integral. So it turns out that only 2 types of geometries contribute as we send the temperature to 0, the extremal geometry itself, and an orbifold of the extremal geometry by a ZC subgroup. These are in some sense analog of the orbifold geometries that were also mentioned in Francesco's talk this morning.
Full theory, or not just in the near horizon? You have the full solution, right?
Yes. We have the full solution for these orbifolds as well. Though the proof that only these 2 geometries contribute to the degeneracy came from a near horizon analysis. So yeah.
So you're still doing an index.
Here I'm computing the actual partition function, not an index. So I'm fixing the charges of the black hole fixing the black hole to have angular momentum 0, and taking the limit when the temperature goes to 0. One can also compute an index, as I'm sure you very well know, by turning on an angular velocity for these black holes. So one can compute these two geometries, both correspond to saddle points of the gravitational path integral. For black holes in n=8 supergravity, they don't depend on each electric and magnetic charge independently. They depend on them through this variable called delta that's known as a U-duality invariant in n=8 supergravity. The leading saddle contributes a factor of e to the pi square root of delta. This pi square root of delta people have computed and is exactly identified as the area of these black holes. And these orbifolds are non-perturbatively subleading, meaning that they don't grow as quickly exponentially with delta. And it turns out that by using supersymmetric localization, one can actually compute all perturbative corrections to this factor of e to the pi square root of delta over c, and one gets the following expansion, where this I is a Bessel function, and this A is what's known as a Kloosterman sum. And the sum overall, the sum over C, is the sum over all possible orbifold angles that are allowed. So this expansion is known as a Rademacher expansion. And it turns out that the sum that I just wrote down converges to an integer, which precisely matches the exact index obtained in stringy constructions of the same black holes. So this provides an indication that, first of all, the index is equal to the degeneracy. And second of all, it provides an exact match between the 0 temperature gravitational partition function obtained from the gravitational path integral and the string theory index.
Sorry, can you clarify this statement? You say index equals degeneracy. That's I mean that's false in equals 4 for finding.
Yeah, I think it's true for these specific type of black holes. In n=8 flat space supergravity that are 1/8 BPS.
What about this graviton gas that Francesco mentioned?
Well, the graviton gas in principle is captured in the perturbative expansion of this pi square root of this Bessel function, because this Bessel function does incorporate all possible fluctuations of the metric around the localization locus.
But then it's not really captured with the codegents. So maybe there's some more information.
Well, it captures the black hole. It captures the partition function of whatever the gravitational path integral computes with the boundary condition that we fix the temperature at infinity, which is what we want to compute in, let's say, SCFT, right?
So when you do this path integral, do you have a boundary, the flat space, or ADS2?
Yeah, here we work with an ADS2 boundary in which we fix the temperature of the black hole by fixing the size of the ADS2 boundary.
So this path integral is already in the very near horizon.
Yes. Okay. Nevertheless, everything that I said so far relies on the prescription of Gibbons and Hawking, and we want to make sure that we're actually counting black hole microstates. So to start, we want to ask, can we actually construct the states that we are counting? And in order to construct them, it's useful to pose a conceptual puzzle first. This conceptual puzzle will be a version of the black hole information paradox that only involves BPS states. So let's pose the puzzle. So suppose we start with a Hartle-Hawking state that we prepare a Euclidean signature by considering the gravitational path integral on a boundary that's an open segment of length beta over 2, where we fix the charges. So we fix the field strength along this boundary. Then people believe that this state from the boundary perspective prepared what's called the thermal field double state. This is an entangled state between the left and right side that takes this form. Now, suppose that we take this thermal field double state and we take the limit when the inverse temperature goes to infinity, if keeping the charges fixed. Then what we are actually preparing should be a maximally entangled state of BPS states on the left and on the right. And these black holes have been constructed last year by with these states by Lin, Maldacena, Rosenberg, and Shan. So this constructs one state, one type of two-sided BPS state that we know of. So how can we possibly construct others? Well, we can take this state and consider matter excitations in this background. We can insert, let's say, a field that's part of our bulk effective field theory, and consider an excitation of this field that's spread at some point on the boundary. But we still evolving with an infinite amount of Euclidean time. Because we're still evolving with an infinite amount of Euclidean time, this new state should also belong to the Hilbert space that's HBPS times HBPS with fixed delta. But it should no longer be the maximally entangled one. So all these black hole states, if I continue them to Lorentzian signature and I'm an observer that lives on the boundary, I would see that all these black hole states are BPR supersymmetric. They have precisely the same mass and the same set of charges, which are given by the BPS relation. But if I started measuring correlation functions in these states, they would all slightly be different from each other. So for instance, if I insert other operators and measure how they back react on the metrics, I would get different results. So now we can prepare a huge set of states by using the fields that we have at our disposal in the effective field theory. Such that when I take the overlap between two states, filling in with the black hole geometry that fills in this boundary when I take this inner product, I can prepare these states such that they're orthogonal by looking at QFT excitations in this background that are orthogonal. So here the indices I and j go from 1 to k. So I prepare k orthogonal states, and it turns out that a calculation shows that even when including back reaction of the matter fields on the geometry and quantum corrections coming from this limit that temperature goes to 0, these states can still be prepared to be orthogonal. So in particular, the following puzzle occurs, which is that the number of QFT excitations that I have available in this background, that's k, can be constructed to be much, much bigger than the dimension of the BPS Hilbert space in a sector of charge delta. And of course, this would be a contradiction because all these states, as I just argued, they have an infinite amount of Euclidean preparation. So all these states should really belong to this Hilbert space. And yet I'm constructing a set of orthogonal states that seemingly is much larger than the dimension of this Hilbert space.
Are they really orthogonal?
Sorry?
Are they really orthogonal though?
Well, yes. That's the question. What goes wrong? The only thing that could possibly go wrong is that they're not orthogonal, and can be viewed as a supersymmetric analog of the black hole information paradox because it's in the same spirit. It's about the fact that secretly these black holes could, at a semi-classical level, have a much larger number of states than naively expected. So the question is, can we find corrections to this inner product that shows that the maximum number of orthogonal states that we can actually construct is equal to the degeneracy of the black hole, that degeneracy squared, where the degeneracy is what was found for the Gibbons-Hawking prescription or for the string theory computation. So the philosophy is that whenever we'll take these inner products, we'll sum over all geometries that satisfy the boundary conditions prescribed by our state preparation. So this sounds a bit abstract, but let me tell you in practice what this means. So suppose now that instead of looking at an inner product, I look at an inner product absolute value squared. So at leading order, these states are orthogonal. The leading order, seemingly leading order contribution are two copies of a black hole, right? Because one copy corresponds to one copy of QI inner product QJ, and there's another copy. But in addition to, and both copies are by construction vanish because these states are orthogonal. But in addition to that, in principle, when I do the gravitational path integral, I have to sum over all geometries consistent with these boundary conditions. And one geometry that's consistent with these boundary conditions is one in which the bulk space-time unites the one copy of QI/QJ to its conjugate. And this is what's known as a Euclidean wormhole.
What if you try to compute a matrix element, not its square?
Which matrix element?
QI/QJ.
Yeah, so if you compute QI/QJ, you'll find that it receives no corrections. And I'll tell you the interpretation of that. The interpretation of that is that there's a very large choice of excitations that I have in my bulk effective field theory. And the excitations, choosing different operators that would construct this orthogonal basis would lead to an average value of the inner product between QI/QJ that is 0. But if I study the variance, namely the absolute value of QI/QJ squared, you will find that it receives a non-zero contribution. And this is very funny because earlier in the talk, I mentioned that the only geometries contributing to the degeneracy were the ADS2 and orbifold geometries. So in fact, these geometries that connect two different boundaries, when you take beta going to infinity, when you take the temperature going to 0, vanish. But they do not vanish in the presence of matter insertions.
So you need this ensemble average.
So I think here the philosophy that there's a difference between the meaning of the ensemble average. We can talk about an ensemble average of theories, or we can talk about an ensemble average of states. And I think either of those is applicable here.
No, but
so
just the fact that this is 0 and this squared is not 0, that's in contradiction with just the basic structure of the Hilbert space, right? So
right. So the question is, what does the effective field theory capture when we say that QI/QJ is equal to 0? What I'm suggesting is that it captures an average over all the possible inner products between states that are naively orthogonal. Here, there are no, but when we take the average of the inner product squared, that's a positive number for any choice of operators. So its average is definitely non-zero. So there's two ways of viewing the problem in the supersymmetry case. The important point is that the exact number of supersymmetric states, the exact number of BPS states, does not vary as we change either the member of the ensemble or the choice of operators, the choice of excitations that become orthogonal. Okay. And in fact, what supersymmetry does by us is that if I study the inner product between QI/QJ squared, it turns out that the sum over possible geometries, the possible wormhole geometries that contribute to this inner product, truncates. Namely, the only contributions to this inner product is either coming from this wormhole in which matter fields connect the two sides, or wormholes in which I have exactly an orbifold, a supersymmetric orbifold geometry on either side of the matter insertion or on both sides. And these are capture the sublitting contribution from the supersymmetric orbifold. So we saw that these states are actually not orthogonal, as Clay suggested, but how do we connect these small corrections that the overlap receive to the actual Hilbert space dimension? So for that, consider the following density matrix. That's a linear combination of the states QI that I constructed earlier, that I said naively are orthogonal. And to determine what the size of the Hilbert space is, of the Hilbert space spanned by these QI, I could ask what the rank of this density matrix is.
K goes over all the positions of these operators in the.
Sorry, who was A?
K, capital K goes.
The K goes over all the possible type of matter insertions and over all the possible locations where I insert them. So naively, if the states were orthogonal, this density matrix would be maximally mixed, meaning that it would be proportional to the identity matrix. And therefore, the rank of this density matrix will be equal to K for all K. And just as before, this would be a contradiction because we could obtain the rank to be arbitrarily large. So to compute the rank of this matrix, it's useful to employ the following quantity called the resolvent of this matrix M. This matrix M is what's known as the Gram matrix between the states QI and QJ. The important feature is that of this matrix M is that the non-zero eigenvalues of M and the non-zero eigenvalues of the density matrix that are constructed are actually the same. So computing the poles of this resolvent, which are essentially the poles are located at the eigenvalues of M, will tell me what the eigenvalues of the density matrix are. And to compute the rank of the density matrix, what I have to count is the number of poles that have non-zero eigenvalue. So I have to compute the following contour integral for the resolvent. So, finger will appear in a question in a second. So the resolvent takes the following form. If I just expand the definition of the resolvent in the geometric expansion, it just has the following powers of lambda. To geometrically represent them, represent what it is, we have to draw what these inner products are. So here by question marks, I simply mean that at this point, we do not know what geometry to fill in this space-time that has this boundary whose proper length is infinite by. So there are two options or multiple options at this order. We can fill the first geometry by disks, but as we saw just by construction, these states are orthogonal unless the two operators that are inserted are the same. Or when I have two copies of the inner product, like I have at order 1 over lambda cubed, I can either fill it by two disks or by a wormhole. And the important thing to notice is that this wormhole has this additional sum over all possible operator insertions that just comes from that expression that I have to consider the sum over all possible intermediate states P. So when K becomes very large, the intuition is that this geometry could start dominating at order 1 over lambda cubed compared to this geometry. So in the limit of large K, I expect the behavior of the resolvent to drastically change. Now, luckily, it turns out that we don't have to use intuition. We can actually solve for what the resolvent is very explicitly using a Schwinger-Dyson equation in which we can write the resolvent as a function of itself. If I just draw all the possible geometries that I wrote down earlier, it turns out, and replace the resolvent with itself, it turns out I can get this for the following Schwinger-Dyson equation. Now, this Schwinger-Dyson equation can be exactly solved. It has this solution that I'll describe in a moment. It has very simple to understand. The important thing to remember is that this lambda, I'm interested in the lambda poles and the poles in lambda of the resolvent. And this function y captures, it depends on the detail. This variable y depends on the detail of my choice of operator, the y. So it depends, for instance, on the scaling dimension of these operators. As you will see, y will turn out to be very unimportant. And this value of e to the s black hole entered through by weighing all the geometries by their respective action, and turns out to be given by a sum over smooth or orbifold geometries of the on-shell action of these on-shell geometries. So it's precisely it's a good approximation for the Gibbons-Hawking black hole degeneracy that I computed earlier. So let's analyze, let's unpack this a little bit and analyze what this resolvent actually gives. So when K is much smaller than e to the 2s black hole, this resolvent has a branch cut that comes from that square root. But notice that the branch cut, the edges of the branch cut are at these points, lambda plus and lambda minus, which are very close to each other in the limit when K is much smaller than e to the s black hole. And are very close to lambda equals 1, meaning that I'm studying a matrix whose eigenvalues are almost entirely 1. So the density matrix is approximately maximally mixed, as one might naively expect from the semi-classical computation. Now, when K is of the same order as the dimension of the Hilbert space, this branch cut becomes very large. And what happens is that lambda minus hits 0. And I'll talk about why that's important in a second. And the fact that it's very large means that the eigenvalues, or some of the eigenvalues, are very far from 1, which means that this density matrix is very far away from being maximally mixed. Finally, when K is bigger than the dimension of the Hilbert space, what happens is that I get additional poles at lambda equals 0 for this resolvent, but there is still a branch field. So now let's compute what the actual rank is by just computing the contour integral that on a contour that wants to capture only positive eigenvalues of M or the eigenvalues of rho. So computing is very easy. We can just compute the contour integral of this quantity, and we get the following answer. The answer is that the number of eigenvalues, non-zero eigenvalues of M, is either K, when K is smaller than the dimension of the BPS space, BPS Hilbert space, or it's the dimension of the BPS Hilbert space squared. So exactly the dimension of the Hilbert space we expected when K is bigger, sorry, typo, than e to the 2s black hole. And and importantly, notice that even though the resolvents, all the inner products depend on the details of the matter fields that I inserted, this contour integral very nicely becomes completely independent of this variable y that I've written previously, meaning that the size, the rank of this density matrix is completely independent of the details of the operator. And that's exactly what one should expect, because the dimension of the Hilbert space of BPS black holes has nothing to do with the matter content in the bulky FD. So where did the rest of the K eigenvalues go when K is bigger than e to the s black hole? Well, there's an additional pole at lambda equals 0 that develops when K is bigger than e to the s black hole, which means that there is linear combinations of states that are exactly, of K states that are exactly 0. These should be identified in modern language as what people would call null states in gravity. And these null states have been subject to a lot of study recently. But here there is an explicit construction of these null states. They're so essentially, even though these states look linearly independent because I insert matter fields at completely different points or even completely different species of matter fields, secretly, there is some linear dependence when I consider a linear combination of e to the 2s black hole of them. Okay, thus the maximal rank of the density matrix precisely equals the number of two-sided BPS states. And this is an explicit path integral construction of a complete basis because of that, because we reproduce the dimension of the Hilbert space. And second, there are complicated linear combinations of this many states, that all these states are naively orthogonal, but in fact, there are linear combinations that vanish. So in this talk, I've provided free derivations for the coefficient of this delta function that corresponds to the number of BPS black hole microstates in a fixed charge sector. First, I reviewed, well, I just briefly mentioned that one can compute that quantity as an index from string theory. Second, one can compute it from the gravitational path integral by using supersymmetric localization and the Gibbons-Hawking prescription. And the third, we can actually provide a Euclidean preparation for all these black hole microstates that are two-sided supersymmetric states. Thank you very much.
Maybe one question. One urgent question. Yes, go ahead.
Just want to make sure I understand. So you define a vector space by this picture of the gravitational path integral. You prescribe some kind of bilinear form or whatever by some rules using this picture. But your bilinear form does not satisfy the usual axioms it has satisfied. So this is still some effective.
Yeah, it's an EFP.
It's not a quantum, it's not a true quantum mechanical system. It's an approximate description of your full.
No, I would say that the EFP captures the average value of these inner products. And to capture a rank of that density matrix, it's enough to study the average value of those inner products.
Okay.
So, sorry?
You're not doing EFT, you're doing an exact path integral.
Yes, but these wormhole contributions should be viewed as, I'm not including all the details about the bulk UV completion. So maybe I shouldn't expect from the beginning to be able to construct all the BPS states exactly. And I think what from my perspective, what these wormholes do is that they provide the statistics of the inner products in the UV completion. So for instance, if I consider these states Qi, Qj, inner product in the UV completion, they would be non-perturbatively small. But if I averaged over all possible values of these inner products, I would get that they on average would be 0. If I averaged over their absolute value squared, I would get the wormhole contribution. If I did this complicated method of the resolvent, and averaged over all possible states, I would get the resolvent that I just solved for earlier. And that's enough to compute the rank of that density matrix that I was interested in.
Okay, we have to stop now. Of the lunch break is by Simeon Hellerman, University of Tokyo, Quinquagenarian and Supersymmetry, and the large R charge expansion.
Is there a, thank you. Is there a MacBook Air? Using MacBook, which wire do I? I don't know. Whoever was using, I mean,
I think I put this wire out of my laptop.
You use this?
I use that one, yeah. I don't think he has oh yeah, he does. No, it doesn't.
The regular connection to the case.
Is that?
No, say USB. Regular old. No. This USB.
Or USB.
Oh, resting.
No, that's not it. You need to connect to USB 3 from USB 3 to Does anybody has a connector?
What kind of connector?
From USB 3 to USB.
USB-A?
Yes.
No. More or less.
Yeah, there's a long pairing a set of blocks. I've never heard of
It's also not in the middle. It's like, but it's third, but it's not third of the. They are flight.
Yeah. The difference here is that the sum over here.
So you took on your way here?
Last time I did it.
Case. In principle, there are higher and higher numbers that are correct.
How many days?
Just 3 days.
3 days?
Where's this resolvent?
Right.
But here, the nice thing is.
It looks beautiful.
And the wormholes in which you also insert one or.
I got it. So he's lost many physical names. But the scenery is different on control. So
Yeah, exactly.
that's interesting.
And the target scale is on the screen here. For him, he studies black holes and colors. The details of the computation depends on the size of the energy window.
Unfortunately, it's not an island, and it's a
Here,
very close to the continent.
you know, because the gravitational pattern is
Usually
well
a
isolated.
Yeah.
There's
Can anybody know him?
It's on the screen here. I don't know.
how much a meter.
It's actually the apologies that Japan kind of
Yeah, but it's
erupted, but it's not correct.
It's not correct. It's actually detached from the.
It's a myth
Yeah, it's a myth.
that the gods created Japan, right? People believe in it.
But more like appendix. Appendix of Korean peninsula.
So, like, when was it connected to, let's say, the Chinese mainland?
Well, it
Millions
actually
and
came
millions.
off. Yeah, came off. So
But when was
yeah. So
The other example, I told you.
tens of billions.
So before mammals were created, like
I-
all the
I should have known.
extinction or later?
There are a lot of dinosaur fossils in Fonzie. It must have been connected.
Well, yes.
Matter, even though the state that you're supersymmetric is not opposite.
But the immigration of people is
More
recent.
Yeah, more recent. It that must be through ocean.
Yeah, that's not through land, and that is kind of we are talking
A long time.
10,000 years,
Yeah.
right? So like genetically, the Japanese and the Chinese must be similar.
Okay, please start.
So today I'm going to talk to you about Quinquagenarian supersymmetry and the large R charge expansion. Quinquagenarian is what you want to think. It's just the it means 50-year-old thing.
Distribution.
Oh, wow. Very fine tuned.
Yeah, I don't, this is very aspirational. Okay. Let me start out by observing why we are all here today. Why is this occasion so important? Why is supersymmetry important? The world isn't supersymmetric. The cosmological constant is non-zero. No super partner has ever been discovered. The young people these days probably don't realize that we used to believe in these things called super partners that were the things you would see when you acted with supersymmetry on an actual particle that you'd actually seen, and you would expect to see another particle about the same energy. So that hasn't really panned out. But maybe it will someday, but not yet. So a lot of us old people think that this is sort of weird and makes us wonder, why supersymmetry is so important. But there is actually a very good answer to this question. Supersymmetry has played such an important role in the development of high energy theoretical physics, particularly quantum field theory. There's a great deal about QFT and gravity and strong coupling we didn't used to fully understand or believe. Many of these things, duality, black hole entropy, holographic duality, SCFT, non-trivial fixed points in higher dimensions, confinement as strong, weak, as dual Higgs mechanism, compactification of space-time dimensions. Many of these were just completely unaccepted or largely unaccepted before being verified in great detail by supersymmetric models. So supersymmetry has been fantastically successful in developing the basic technology of high energy theory. It's rigid enough to allow exact analytic computation, while at the same time being flexible enough to allow to embed almost any effect you might want as a calculable effect in a supersymmetric model. Supersymmetry is really in the sweet spot between specialness and genericity. That's, I think, why it's been such a theoretical touchstone. But now people are turning towards different sorts of questions, not how does QFT work or any individual QFT work, but turning to higher order questions about the large scale structure of the space of quantum field theories, for instance, conformal theories, as explored by the conformal bootstrap.
And these questions are so generic, there's still a big gap in understanding. Can supersymmetry help bridge this gap, or is it too wide? Well, you should keep this question in mind. This is a little local reference for those who something that happened around SUSY 40. Speaking I-35 Minneapolis. With this in mind, let me now discuss the large quantum number expansion so that I can offer it as a possible way forward in this respect. So for the last several years, there's been a systematic development of the idea of the simplification of otherwise strongly coupled quantum systems in the limit of large quantum number. By otherwise strongly coupled, I mean outside of any simplifying limit where the theory becomes semi-classical, or possibly in such a limit. But with the quantum number taken so large, the system behaves differently than you might otherwise have expected. Now, is this even a subject? You might be asking. The answer is yes. In some sense, it's an old one. Examples have appeared stretching very far into the past, all the way back really to the 1800s. In some sense, this is fair. I hate to omit. But in some sense, this is all a revitalization of the old idea of the correspondence principle. And it's been explored and realized in a sort of accelerating tempo in the last couple decades, and maybe a bit more self-consciously in the last 7 or 8 years or so. The ideas in some sense haven't changed, but there's been a more conscious development of this line of research. And today I'm going to specifically review some stuff that where it's been applied in the case of theories with extended supersymmetry. But there's also been a huge amount of fascinating work in this area in the last few years that I haven't even had time barely to read all of it, let alone summarize it here. But so what is the large quantum number expansion for? Largely to answer the same kinds of questions as the conformal bootstrap, to systematically and efficiently analyze quantum theories where in situations where other tools aren't applicable, where there's no exact solution or recoupling parameter. We'd all like to know, what does theory space look like? Bootstrap has been extremely helpful in giving some answer to this question. But in extreme limits, not only in theory space, but in the space of states or operators in a given theory, conventional bootstrap methods tend to break down, except in one special case, a large spin in a single plane. But generally, when one asks about a large operator dimension, large energy, large spin in say in multiple planes or large internal quantum numbers, conventional bootstrap methods slow down, even for very simple questions. Although for internal global symmetries, there's been a bit of interesting progress a few years ago. It still has not been fully, I think, followed up. Should be. So in many cases, perhaps all cases, these limits are accessible to new kinds of EFT in regions where bootstrap methods slow down. So what could we try to do? Well, there are sort of more and less grandiose goals you could set your sights on, but this talk is really going to be on the most modest possible goal, which is to translate these behaviors in these EFTs into bootstrap terms and to say what it means for CFG data. The simplest possible example is the case of the O2 model, the Wilson-Fisher conformal O2 model. One can ask about the weight of the lowest operator of O2 charge J, translating that via radial quantization, which is always going to be our approach here. you can ask, what is the energy of the lowest state of charge J on a unit S2? So there's a complicated renormal, or not that complicated, but just a detailed renormalization group analysis showing that the large charge sector is controlled by a very simple effective field theory with a derivative expansion whose leading term in the expansion is just this thing, which you might say is the second simplest possible Lagrangian a human being could ever write down. Simplest Lagrangian is the one.
Third power,
Yes.
then I would say why it is the simplest.
It's the second. It's the second simplest. The simplest Lagrangian you could possibly write down is from a free massless scalar, which is grad chi squared. Well, this is the second simplest. It's grad chi cubed. And I'll leave as an exercise what the third simplest Lagrangian is. The immediate consequence of the structure of the EFT is that the lowest operator is a scalar whose dimension goes as the 3/2 power of the pure charge, where this c to the 3/2 can be written as a simple function of this EFT parameter, this Wilson coefficient B. And then the leading order EFT predicts more than just the leading power law. It predicts quantum loop effects and so on. And also, the dimensions and spins of degeneracies of the excited primaries. And what's really striking is that just a small number of Wilson coefficients are extremely predictive, predict the first several orders of the large expansion for huge number of states.
What is the dimension? I mean, how many space time dimension you have?
Yeah, this is in 3 dimensions. It works the same sort of in all dimensions between 2 and 4, but 3 is the one which doesn't have any.
No, because when you have D with index, to organize a cube is some problem, right? Because you should have convert the indices, right? D acting on chi. D mu acting on chi, I should multiply by something.
It's even square absolute value. Square root of the
Square root. Yeah. So it's not. So in some sense, it's contains fractional power, right?
Yes.
In terms of.
Yeah, but that's never. There are frequently asked questions. I'll get to that in the Q&A. But this is turns out to not be an issue. At any rate, the low-lying large charge sector is described by this very simple Lagrangian EFT. Whose propagation speed is fixed, the frequencies of the oscillators are fixed, the energies of the excited levels are fixed. For instance, the first excited primary has a spin greater by 2 and a dimension greater by square root of 3. Right? Who ordered that? But that's what it is. Subleading terms can be computed as well. These terms all have a natural hierarchical organization in the inverse charge. And at any given order in derivatives, there are only a finite number of such terms. So this theory is very predictive. We'll see soon that it's also very accurate. There's only one subleading term contributing with positive powers of the charge, and in particular, there are no terms scaling as j to the 0. So the order j to the 0 term is universal, it's not renormalized, and the large charge expansion at the first several orders goes as c sub 3/2 j to the 3/2, c sub 1/2 j to the 1/2 minus 0.09372556 and so forth. Please remember this number is going to come back in a few minutes when I brag about how accurate the expansion is. There are no sort of fudge factors or ambiguities in these universal relations. Similar predictions have been made for E coefficients and so on. Among the most tractable universality classes are large R charge and extended superconformal theories with moduli spaces of supersymmetric vacuum. Simplest case is the three-dimensional n equals 2 superconformal fixed point with superpotential XYZ made of 3 chiral superfields. So without loss of generality, you can consider the X branch. The big challenge in these large R charge theories is to find when you add extended supersymmetry is to find any quantity. It's not to be able to find quantities you can control. It's not to be able to find quantities that you can get an accurate prediction for. It's to find quantities such that the expansion isn't completely boring, right? So this theory has an exact chiral ring. So the large R charge expansion of the dimension of the lowest state is automatically boring. It's just J with no corrections. At least that's the prediction from supersymmetry, not as a large R charge thing, but just as an exact thing. The second lowest state is also BPS. It's a scalar semi-short. So its large R charge expansion of its dimension is also boring. But we'd like to at least test these large R charge EFTs by comparing explicitly with these exact supersymmetric results. And we'd also like to maybe compute something more interesting. So the more interesting things would be controlled by D terms, but the leading D term is just the kinetic term for the field. So there's nothing really there. We can exchange X for an approximately free chiral superfield in the effective theory of the X branch.
I think it accumulates the charge. It accumulates the charge so you can expand them.
Exactly.
Large charge.
It's a lot, yeah, it's a very large. Great.
It might affect your finely tuned timing.
Yeah. Does anybody know the password? Just the wrong.
This is really remarkable.
Yes. Trivial. Large R charge expansion depending on the D terms. So from that, we get a kind of
I don't know because I had a freeze on me.
Oh, there. Still working on logic.
stop beating.
It's
still spin.
Okay.
Okay, yeah, it's still doing that.
Yeah.
Okay, so I'm just going to say what the results are. Results checked. So one can check these predictions in a large R charge EFT made from the field generating the X branch. And the result is that the lowest primary is equal to J up to 3 loops. The second lowest is equal to J up to 2 loops.
J plus 1.
Excuse me, J plus 1 up to 2 loops. And the third lowest is equal to J plus 2 plus some number, depending on the Wilson coefficient, which I will define and show you in a moment, times J to the minus 3 plus order J to the minus 4 and higher. With n greater than or equal to 2 SUSY. So 4-dimensional superconformal gauge theories with a 1-dimensional Coulomb branch. And then we considered 2-point functions of Coulomb branch operators. So where the curly O is the generator of the chiral ring. Of the Coulomb branch chiral ring. Okay. Right. So these can be computed via supersymmetric localization via an algorithm worked out by Gershkovitz, Gomes, Pufu, Komargadsky, and a couple of other people who are on my slides. Oh, okay, good.
Sorry,
Thank you so much. Yeah, thanks. So Right, so here we are. So I'm now on to four-dimensional superconformal theories with one-dimensional Coulomb branch. Some of these are Lagrangian with marginal coupling, some are non-Lagrangian with more abstract descriptions, but they can all be treated on equal footing. The Coulomb branch chiral ring in a rank 1 theory looks like this. As far as we know, the chiral ring is all freely generated, always freely generated in one dimension. So at large charge and radial quantization, these states correspond to classical solutions on the sphere, where the Coulomb branch scalar gets a bev proportional to root j over radius of the sphere. So for Lagrangian theories, you can take the chiral ring generator to be trace phi squared. For non-Lagrangian theories, it's some other fractional dimension. But then we can always write the large J effective action in terms of this chiral n equals 2 chiral superfield. So the only important term in the EFT, other than the free kinetic term, is this anomaly term, which was first identified by Dine and Seiberg as the unique higher derivative term in n equals 2 theories of rank 1. The unique of 4 derivative term. Its coefficient is completely set by an anomaly coefficient, the Weil A anomaly. So I'm going to skip over all these comments. So you can compute. The interesting thing is to compute, because they are verifiable by localization, are these Coulomb branch correlation functions. The easiest things to compute are the unnormalized ones, so the ones where you don't divide by the partition function, but you do scale out the distance here. You can logarithmize the operator insertions and call them sources localized at particular points. And so you can just treat this as an EFT computation performed in this Coulomb branch EFT. The simplest things to compute are these double differences, these double ratios. These can be evaluated straightforwardly in principle as functions of the R charge J and the anomaly coefficient alpha using Feynman diagrams with no further input from the CFT. In practice, it's easier if you use tricks. We used many various tricks, which I won't go into methods here. But the form of the expansion is that these Qs, these logs of the unnormalized correlators, have the expansion AN plus B, where N is the R charge. These are coefficients, these are numbers that are to some extent scheme dependent and also depend on the marginal coupling. And these power law corrections are completely independent of the marginal parameters. So that's why it's a little bit boring to check these in perturbation theory. But I'll come soon to what I think is interesting. So these are the sort of diagrammatic calculations, which in principle you could check all of these predictions order by order. Of course, actually directly evaluating multi-loop diagrams in the EFT is hard. We used a large number of tricks to do it, but nothing conceptually sort of interesting. The result is that the power law corrections are completely given by a gamma function. And then there are exponentially small corrections. So, well, I'm going to skip all of the mention of the detailed verification of these large R charge predictions in the O2 model and some other models, but by now they've been verified to great accuracy.
0.09 thing, it was verified in your opinion?
No, not in the O2 model.
It's not precise enough yet.
It's not precise enough yet. It's certainly consistent with it. It sits right, if you write a sum rule, it sits right in about the error bars for that sum rule, but I don't think it's, but the universal coefficient has been verified in some other models in the same large R charge universality. And then, yeah, so there are some recent results that are even more precise, but still, I think, not quite precise enough to get this universal coefficient, unfortunately. Also, there's good agreement with bootstrap, even at very low values of the R charge. Anyway, so for free gauge theory and n=4, these are very easy to check and verify. There are no exponentially small corrections. In superconformal QCD with 4 flavors in gauge group SU2, there is a much more non-trivial check. There's no closed form, even though in principle, this can be computed numerically by an algorithm invented by Zohar and others. And the numerical computation, and actually I think some data we directly stole from them, allows us to check against the large R charge expansion. So as a function of tau and as a function of the R charge, and you can see going to weak coupling makes the predictions worse, and going to large R charge makes the predictions better. So it really is a sort of duality in that sense. And then finally, one can subtract out the power law corrections and ask about the exponentially small corrections. And you can check against an exponential ansatz in which these power law corrections are associated with virtual effect of a BPS particle. So I'll show you principle. What is the right? So in radial quantization, these exponentially small corrections are supposed to be associated with the virtual trajectory of a massive hypermultiplet along a spatial slice of the sphere in radial quantization, and they match extremely precisely. This is just the EFT solution without the exponentially small corrections, both as a function of R charge and as a function of the coupling. And then again using EFT inputs as well as matching with a perturbation theory, double-scaled perturbation theory in a way invented by Grassi, Komargatsky, and Paisano. We were able to fill in several subleading corrections to the several subleading corrections to the large R charge expansion of the exponentially small correction itself. So this is the log of the exponentially small correction itself. This is an ansatz, a series ansatz for it, and these coupling functions are filled in by supersymmetric recursion relations obeyed by the correlation functions. And so you can solve these order by order using the recursion relations up to whatever order you like. We've now gone several orders above this. S is the inverse infrared gauge coupling. This is a plot of the accuracy of the fixed coupling large charge estimates of the MMP function through next to leading order, plotted as by the MMP function, I mean the exponentially small correction, plotted as the number of digits of accuracy of each of the estimates. So each 2 ticks up on the graph here is 1 improvement in accuracy. So every additional order one adds to the exponentially small correction gives an improvement of accuracy, indicating, I think, very strongly that this is the correct large R charge expansion. And then here are some just tables of numerical goodness of the estimates. This of the exponentially small correction itself. Even at R charge 10, you can see the accuracy is about 1 part in 10,000. And this is the accuracy of the exponentially small correction itself. And then up at R charge 120, I don't know, the accuracy is extremely good, about 10 digits, as you can see. So we started this talk by observing that supersymmetry has been important for establishing the validity of various non-perturbative tools for doing high energy physics. It's allowed us to nail down beyond doubt the basic picture of large quantum number physics is generating an independent sort of loop expansion that's orthogonal to conventional perturbation theory, in that it applies to a fixed theory rather than a family. We've established its validity in perturbation theory, by which I mean 1 over R charge perturbation theory, by verifying it at the level of power law corrections, reproducing the expected BPS cancellations to the orders we can check. And even at all orders in large R charge perturbation theory, matching the all orders power law formula with SQCD by localization, and even down to the exponentially small corrections. I'd like to think that these results can go some way to establishing the validity of the large quantum number expansion as a thing that makes sense, defining an asymptotic expansion with some sort of interesting resurgence properties. Please ask me about that if you're interested. It gives us a new way to understand the direct connection between low-lying operators and high dimension operators, with the latter being literally generated algebraically by the former. And also a precise way of understanding the connection between large dimension states on the one hand and vacuum moduli or semi-classical states on the other hand. And these are connections that should have definite analogs in large charge limits of non-SUSY theories, but we don't know them yet. So at the moment, this bridge will only take you halfway there, and we are still in the process of completing it. So thank you.
Yes. In supersymmetric theories, there are large charge sectors, large charge sectors of which you have a large degeneracy of ground states.
Yes.
Does your approach of effective filter work in situations where there are multiple ground states in that sector?
Yeah, it does. I mean, we were specifically considering rank 1 because that's the case in which the equivalent branch doesn't have an entropy. But the EFTs apply, equally well to cases where they do. The question then becomes like, what do you actually ask, right? There's no longer a very canonical question. You can ask questions.
Operators above the BPS bound would still be a very interesting question.
Sure, but then you have to say which ones, right? Then there's no second lowest operator. There's a whole degeneracy of second lowest operators and so forth.
Wait, why would there not be a second lowest?
Yeah,
Like, why would there not be a non-BPS lowest operator?
No, there's not a the second lowest. There's a whole bunch of second lowest. You have to have
the degeneracy in the not for non-BPS operators.
No, counting the degeneracy is easy.
Yeah,
the degeneracy is not a problem. That's been counted like many that can be counted a million ways. The question is, they're more
BPS operators. Sorry, the non-BPS operators.
Well, I mean, I don't know. For first excited non-PPS operators, yeah, no, I guess you could ask that question. Yeah, you could ask it. I mean, it's easy to answer. I'm not. There's no question about whether it's answerable. It's just is it interesting or boring? I don't know. If it's interesting to you, it's interesting. That's what you were actually asking. In which case, I'm sure that it's interesting.
Probably it's not in a superfluid phase. I would say nothing is known about it. But it's not in a superfluid phase.
It's close enough to a superfluid that it's.
No, I mean the black hole degeneracy is not a superfluid.
No, black holes are really
But I
different.
think that's what we're asking about.
Yeah, that's exactly what
Nick is asking about the black hole degeneracy.
He didn't say black holes.
large charge is what you.
No, there's large and there's large and there's large. There's large. There's large R charge where the R charge is large but not as large as n, not as large as the rank, and there's large R charge where the charge is much larger than the rank. In the second limit, it's close enough to a superfluid to a.
Yeah, when R is much, much bigger than N squared, probably superfluid.
Yeah, so I mean, mostly what I've been focusing on all along is the case where there's no other parameter or where J is much larger than any other inverse loop counted parameter, such as 1 over N squared. But of course, for theories with other parameters like N or coupling or whatever, there is a very interesting story about how you interpolate between different largenesses of J, and this comes under the heading of double scaling limits, which, well, I didn't even have time to talk about the things I wanted to talk about. But, yeah. So how large is a very important question. I specifically chose theories that avoided that issue.
Do you think the approach extends beyond that? Or?
It does. I mean, there's this technology called the double scaling limit, where you take the R charge and the other inverse loop count parameter, both very large, keep their ratio fixed, and then interpolate as a function of the ratio. And then that entire interpolation is under semi-classical control. Grassi, Komargatsky, and Taizano did this for super QCD, and people did it for non-supersymmetric theories. So yeah, I mean, there's no problem in principle when there's another parameter, but you know, the question of what you actually ask becomes more involved.
Okay, we have to think this speaker. Lunch break.
You're the next speaker after the lunch, right?
And there are a large number of other places where you can eat if you go in this direction, and maybe you the right when you hit the rails. Where the tram goes, it's called the Washington Avenue. And if you go in this direction and this along the Washington Avenue, you find something to your taste. Another option, you can just go to the website of the
I have.
Okay, I suppose that. Right.
It's what I'm temperature. It's been getting averaging